Hello everybody. I'm Steve Randall, if you don't know me. Sort of been doing conferences for a little while now. This is my dad. He's helping me organise this year's conference. It's been a huge help. We wouldn't have it able to do it without him. The first thing in the agenda is like to turn down the sound on my laptop because it's distracting me. The first thing on the agenda is basically fire safety and where the exits are and that type of thing.
Hello, so I'm the duty manager for today. There are no planned fire drills, so if you do hear an alarm, react as if it is a true alarm. Fire exits just out here through the garden. There is an additional one just behind you through the small meeting room. The meeting point is up by the Yonex building by the Santander bikes. And I am your fire warden, so I will be in my fetching high-vis jacket. You can follow and listen to everything I say. If you need the bathrooms, they are just through the cafe and outside the double doors. Cool.
Brilliant. Okay. Thanks.
You.
Right. I think the only other thing to say is about the toilets, if you need them, which are just out there. If you haven't found them already. Did she?
No. She said bathrooms.
Right, okay. Format for today is essentially a number of presentations. About every hour and a half we have a break, something to eat, drink, like tea, coffee, biscuits, and then at lunchtime we've got about an hour for lunch. So with that, we will just move on to the format for today. There's been a bit of a change where it's around about 11 o'clock just after the first break. Peter Rutherford was going to do a presentation on launching in London, but he's having to fill in for somebody at the moment, so he's not able to make it today. So instead, you've got me and Dave as well. Dave will be on twice there, one after the other, with a bit of a break with me in between. But we just added in a landing swap presentation, which I put together last year, but never gave. So it's a bit of an opportunity to do that. Right. Okay. Well, with that, I think we're into the first one, which is Ryan.
Ryan White. Okay, I would like to invite Ryan White, the head of the Imperial College Hackspace, to which we got the venue, to give a quick an introduction to
put that on somewhere.
The space we have here at Imperial College.
Hey everyone, how's it going? So the Imperial College Advanced Hackspace is part of the Invention Rooms, which is where we find ourselves at the minute. Let me just get this mic sorted out. So we're in the Invention Rooms building at the moment. This is part of the Imperial College White City campus. We're trying to build something out here that's sort of unprecedented in scale for universities, at least in the UK and worldwide. So the Invention Rooms comprise of 3/4 of this building. We're down in sort of that end of it right now, which is a community space, a cafe that's open to the public during the week, and this room, which is for community events and for hire for folks who want to come and do things exactly like this. So this is run by the Imperial College Outreach team, who sit upstairs and sort of manage outreach within the White City area. Next along is the Reach Out and Makerspace, and in there it's a workshop, well equipped to deliver programs for local school kids, so that they can sort of get their hands-on prototyping experience. Maybe if they haven't had as much access to a DT lab as some of us I'm sure have, they can get that access through here with programs run by Imperial College and supported by students and staff at Imperial College. So we can sort of reach out and share the research that's going on in Imperial College with people in the local community. Next along is the bit that I have the pleasure of running, which is the Imperial College Advanced Hackspace. And in there, we want to make it as easy as possible for anybody at Imperial College to make anything. And that ranges from chemical, biological projects, prototyping in synthetic biology, molecular biology. We've actually got 3 teams in the bio lab working at the moment on some really cool projects. One of them is called Census. They're developing a sort of sensor for detecting the concentration of like a drug for rheumatoid arthritis, using like novel spectroscopy techniques. There's another team that's entering into a biomod competition, which is a US synthetic biology competition, and they're working on a lipid membrane with DNA nanopore in it that will allow the targeted delivery of cancer drugs. And there's another team in there working on developing lower cost growth factors for lab-grown meat. So really interesting projects happening in the biohack space. Then our electronics and digital manufacturing lab, where we've got a suite of 3D printers, laser cutters, vinyl cutters, and workbenches with the requisite suite of electronics test equipment for developing sort of electromechanical prototypes. And then coming online later on this year, we've got a large wood and metal workshop where we're going to have CNC and manual machining, turning, welding, metal fabrication, and also woodwork as well, so a large format CNC router, band saws, and that sort of thing. The idea is that we make these facilities available to anybody at Imperial College in order that they have the means of innovation. So this is some photographs of some folks working on various projects in our various spaces. So you can see the yellow room, which is our electronics and digital manufacturing lab, the wood and metal workshop, and the bio lab represented there. So, like I said, we want to give everyone the means of innovation. We want to turn the entire college population into a population of innovators. And we want to support existing communities like the Imperial College Space Society with their projects and development of prototypes for their research activities, their taught programs, and one of our main focuses is on enterprising activities. So we want to make it easy for people to make an early stage prototype so that they can go out into the wide world of investors and say, hey, can I have some money to develop this further? As I said, we've got a huge range of facilities at the Hackspace, including a co-working space upstairs, which I didn't mention. And we want to make it so that it's not just make the facilities accessible, but also offer training and sort of de-skill the processes in order that they're more accessible to make it easier for more people to build more cool stuff. We've got about, depending on how you count it, around 3,000 members. We've got 1,200 people in our Slack group, for example. We've got about 200 regular visitors to the space each month. And that's obviously changing as the university is a dynamic sort of place, naturally transient population, and people just come in right around the busy times of term just to smash out stuff in our workshop, and it's really nice to see that buzz. So we also host maker events. So we try and run programs. One of the most successful ones that I'd like to speak about was called Hack Medicine Mondays, where we focused on making the means of prototyping available to medical students and people in the life sciences, where they went from scratch to build a syringe pump. It's a very basic device for people who are competent with electromechanical assemblies and laser cutting and 3D printing already. But for folks who've never used that sort of technology, to bring them up to speed with that and make the tools available to them is a really powerful thing for them to understand and then take back to their labs. If you've got a research project that you're working on and you need some widget to fill a hole, it's really easy to go out and spend £1,000 at VWR or whoever to get that widget, I'm sure. But if you can get in the lab and make it yourself and iterate on it a few times, you could probably make it even better. We have a strong members network, as I said. Everybody communicates on Slack and talks about the projects that they're working on. Some of the successful projects that have come out of the Hackspace, as well as the ones that are being worked on at the minute. I'll just talk about one of them. It's one of my favorites. This here is called Bladebug, and it's an autonomous sort of hexapod robot with suction cups on the legs, and the idea is that it will climb around on wind turbine blades to inspect the leading edge of them, and eventually one day do a little bit more with them. So they've graduated from the Hackspace and they're working down the road now and doing some really interesting things as part of the larger group where they're trying to deliver those on autonomous ships, put them on the wind turbine blades with autonomous UAVs, and then do the whole cycle of maintenance on these wind turbine blades autonomously. And at the moment, you can imagine it's rope access technicians who do that work, and you wouldn't find me over the North Sea on the end of a rope. So that's the Hackspace. Thank you all for coming down. Really good to see such a group of people here to talk about something as interesting as high altitude stuff. Just so that you know, I'm very happy to run some tours around 12:45 when we have lunch. If anybody's interested in seeing the Hackspace facilities, just come and find me, and I will show you around about lunchtime. So thank you very much, and welcome everyone.
introduction to the Imperial College Advanced Hackspace and the invention rooms. And our next talk is by Mark Jessup from Australia. It will be a remote presentation over Skype. Just give me a second to set up the hardware here.
So hopefully you can all hear me as well.
Yep.
Okay, I'm going to mute my audio just momentarily, but we'll see how we go. All right, let me just go to screen sharing and we'll get started. All right, hopefully that is now working.
Yep, perfect.
All right, good morning all. It's actually almost 7 p.m. here in South Australia. My name is Mark Jessup. I've been involved in pilotship for almost 10 years now. Our local project for us has currently done 53 balloon launches, and we're about to have our 54th pretty soon. But today I'm here to talk to you about Radiosonde Auto RX, also known as how to overload habitat with the Radiosonde. So my talk will be a bit of an overview on radiosondes themselves, why we want to go hunt them, a bit of a look at some common radiosonde types you might encounter in Europe mainly, a bit of a discussion on Radiosonde Auto RX, the software that I've developed, and also Hub, which is some utilities online to deal with processing of radiosonde data. So, given this is the UK House Conference, I'm going to assume that you're all somewhat familiar with how a high altitude balloon works. And so you know what that big white thing in the screen there is. So, and we'll just focus on the radiosondes themselves. So, a radiosonde is a meteorological instrument which collects data on the Earth's atmosphere and transmits it back to the ground via a radio link. Essential radiosondes nowadays have temperature sensors and also a GPS receiver to measure wind speed vectors. This used to be performed by radar tracking, but nowadays it's all GPS. Sometimes you'll find payloads like ozone sensors and radiation sensors as well. The majority of radiosondes transmit somewhere between 4 and 406 megahertz, though in the US you do find them on 1.7 gigahertz as well. As of last month, there were 700 radiosonde launch sites. Hang on, let me check what's going on here. Is my screen sharing working?
Yeah.
Is one all working, guys? All right, all good. No problem. Well, as of last month, there are 700 radiosonde launch sites reporting to the World Meteorological Organization, most of which are launching at least once a day. So, why do we bother chasing these? Well, of those 700 radiosondes that are launched per day, or more actually, precisely none of them are being actively recovered by the launching organisation. So we can go and help clean up the Met Bureau's mess and shame them on Twitter. It's also great practice for your own high-altitude balloon launch, and it lets you test out your car systems and receiver hardware in a situation identical to a real balloon chase. Depending upon the radiosonde you're chasing, you might be able to reprogram it for use in one of your own flights. And they also make really good Christmas decorations. So there are many radiosonde types used worldwide. I'm going to focus on a few of the ones that you, as the audience, are more likely to encounter. So first up, the Lockheed Martin LMS-6. This is a true US radiosonde.
Mark,
It's big. Yes?
could you give me a second? Let me. Unfortunately, the screen is not synchronized with the projector. So give me a second. I'll try to sort that out.
You know, if you want to go back a few slides.
Yeah. Let's see what's going on. Second screen only.
screen share again.
Okay, I can see that seems to be working fine.
All right, how's my audio? Is that working?
Yes, yes, it seems to be fine.
All right.
Thank you.
Excellent. All right, so I'll go back from where I started, where I left off. So as I mentioned, there's many radiosonde types used worldwide. Now I'm going to just quickly discuss a couple of the more common ones you're going to encounter in Europe and also in the US and Australia as well. So first up, the Lockheed Martin LMS-6. This is a US radiosonde. It's big and it's heavy. It's also a very, very old design. It even comes with a little roll-up bag so you can send it back to the National Weather Service. However, given the case is hot glued together, I have no idea how they plan on recording these things. It comes in 400 megahertz and 1680 megahertz versions, transmits at 9600 baud and uses an ancient, and I mean obsolete for about 5 years, microcontroller and a simple GPS receiver. Now the Vaisala RS-92, which you guys may have seen before, is an interesting beast, still flown in a few places around the world, including the US, Australia and Brazil, but it is being phased out due to it being well and truly obsolete. What's interesting about it is the main microcontroller and the radio transmitter IC are entirely custom silicon designed just for this particular product. Makes reverse engineering pretty difficult. It also doesn't have a complete GPS receiver on board. Instead, the position calculations are actually performed on ground. The little L-band helical antenna is pretty cool, and that can be reused for reception of Iridium satellites and the like.
Sorry.
Looks like we have some network issues. Sorry,
Okay,
guys.
I think it's working fine. I'll leave it
I will
until
note that
it's... Yeah.
the Australians in the audience, I am on NBN. That probably explains it.
No, don't worry. You may carry on. Yeah. There you go.
All right, let's give this another go.
Yeah.
All right, your video is also pretty broken up as well, so I'm not sure how this is going to go.
No, we can hear you and see these slides.
All right, no, not a problem. Well, next up, the GRAW DFM09 runs at 2500 baud, which is very, very odd to me, and your video is also stopped, by the way. It's got a pretty capable microcontroller and GPS receiver, but I'm pretty sure no one's actually been able to reprogram one of these yet. There's also a newer and a smaller version, the DFM17, which is already being seen in the wild as well. And there we go. So the internet, the IMET4 is a really cool radiosonde. It has a very powerful STM32, a modern U-Blox chipset, a Series 8, my goodness, and a very capable TI radio chip. Unfortunately, they're pretty, they're not very common. They're only used in Belgium and in Israel. Unfortunately, IMET chose to have this on transmit 1200 baud AFSK, think APRS, as opposed to straight FSK. This immediately throws around 8 dB of power due to the double modulation. It also doesn't transmit a unique serial number, which makes dealing with telemetry from these a real pain. The media modem N10, mostly found in France, kind of bucks the trend a bit. It uses a TI MSP430. The firmware is not reprotected. You can dump it, and you can modify it so it will transmit on the amateur radio 70 centimeter band. In fact, one of these was used as a primary tracker in an amateur launch out of France a few months ago. Last but definitely not least, the Vaisala RS-41, or as I like to call it, the STM32 development ball that literally falls from the sky. According to the World Meteorological Organization statistics, the RS-41 is launched from 186 sites around the world at the moment, accounting for 30% of all worldwide radiosonde launches. It is the most common radiosonde out there. And being the most common, it's had the most amount of reverse engineering applied to it. Thankfully, nothing like its predecessor, the RS-92, and apart from the sensor stalk, uses off-the-shelf parts. So these parts, being a STM32 microcontroller, a U-Blox 6 GPS, and an SI4032 radio, which are all getting on a bit now, they're all pretty much approaching end of life, they've been used in the partnership learning community for quite some time. They're very well known. The temperature and the humidity sensors are a bit of a mystery still, but there has been some good reverse engineering work done on these, and hopefully it won't be too long before we get to see some software that will drive them. You also get 2 free lithium AA batteries, usually at about 80% capacity if you recover the song shortly after landing. Reflashing the RS-41 is ridiculously easy, as Vassala handily broke out programming pins to a header at the bottom of the PCB. Grab some firmware off GitHub, you get an ST-Link programmer, hook up a couple of wires, away you go. You've now got your own pre-tested balloon tracker. So all of the radio songs that I've shown so far can be decoded by multiple software packages. SonMonitor is one that's been around for a very, very long time, about 12 years actually. However, it's closed source and costs about 25 quid. The developer is a very nice guy though. RS-41 Tracker is a fairly recent one, targeted specifically at RS-41s as the name suggests. It has a link to a map and it can do some APRS uploading stuff. It is free, but it's also closed source. DXL APRS has been around for a while, and that will decode RS-41s, RS-92s, and DFM radio songs. It's open source. But its code base is best described as opaque, and it's very difficult to modify. When I first started seriously getting into decoding radio songs, none of the above did quite what I was after, or in the case of RS-41 Tracker even existed, so I ended up writing my own. The main reason was because here in Australia, radio song frequencies are not particularly consistent. Over in Europe, you guys have got some coordination. Here in Australia, not so much. Transmit frequencies would change from launch to launch. I needed to have a way to scan the radio song band to automatically find and decode them. So I based this around a set of open source radio song decoders written by a guy only known as RS1729 on GitHub, and I wrote Python code to automatically scan, decode, and upload telemetry. It supports all the song types I mentioned in the presentation, with support for more being actively developed. I've also recently started to use David Rowe's frequency shift King demodulator, which helps with demodulation performance. When I presented on this software at the beginning of the year at LinuxConf, there were 60 stations in operation. As of today, that number's 132, which actually kind of freaks me out a little bit that there's people running my own code. Anyway, to get all the codes available on GitHub, the latest guide, the link that you can see there on the slide, hopefully. To get started, you need some kind of Linux machine, an RTL SDR, and an antenna. I recommend running AutoRx on a Raspberry Pi, along with one of the version 3 RTL SDRs. There are also excellent preamplifiers designed specifically for the radio song band available from Ukutronics. I'm not sure that Anthony's in the audience, but there's your plug. Using one of these is not mandatory, but it does help. So it's a bit of a flowchart showing how AutoRx operates. On the left, we have the RF hardware, which is capturing the radio signal and converting it into digital samples that we can then process. The first thing AutoRx does with all this data is scan through the radio song band and look for the signals which are above a set signal-to-noise ratio threshold. Once it has a list of peaks, it looks at each of them in turn and attempts to determine if the signal is a radio song or just noise. It does this by cross-correlating the received signal with a set of known reference signals. If the correlation score is above a certain threshold, the signal is more than likely that particular type of radio song. AutoRx then locks onto the radio song and starts decoding it. The received telemetry data can be uploaded to the APRS internet service for viewing on aprs.fi, to the Hub tracker via our SonHub page, which I'll get to a little bit later on, and also to local mapping services such as my ChaseMapper browser-based map, and also Dave's LCARS mapping application also supports it, I'm pretty sure.
Yep.
Good. Thanks, Dave. AutoRx also has a web interface, which you can look at, which shows the results of the scanner steps. So that little graph at the bottom shows the 2 peaks that it's detected. It'll show any telemetry currently being decoded, and it also shows where the radio sond is on a map and where you are. If you want to decode more than one radio sond at a performance versus the signal-to-noise ratio that being fed into them, along with the theoretical performance of uncoded frequency shift keying. And yes, they're all performing better than theory. This is because all the radio sons we are decoding have some forward error correction in use, which gives us a few decibels of coding gain. The point here is that the modems that I'm using are performing as well as they can. So all of these is down to your receive hardware, which sets the limit of your decoding range. So as I mentioned before, all the data that's uploaded to Habitat goes via our SondHub service. So SondHub is a whole lot of Amazon Web Service magic, which gives us control over data flows. This has been put together by Michael Wheeler, my co-developer on AutoRx. He's an AWS guru in his actual real job. So this lets us do things like restricting uploads from old versions of AutoRx, so we can rate limit our users that might be uploading too quickly. We can also store a copy of the telemetry in our own database. So the specifics of what's going on within AWS is pretty complicated, as you can tell by this overly complicated diagram. And this part is more Michael's doing, but I'll do my best at explaining what's going on. So SondHub is acting essentially as a proxy between clients and the HabHub servers and the Habitat database. Clients could be AutoRx stations, or it could be just anyone visiting sondhub.org. When someone visits sondhub.org, they get redirected to the tracker website. However, we automatically set the filtering to be RadioSonde specific, and we also replace the Google Maps API key with our own. This lets us avoid using up the HabHub API key. All telemetry uploads go via what's called AWS API Gateway. This is where we can do our filtering based on version number and call sign. Telemetry is buffered into a database, DynamoDB, before being uploaded into HabHub. This lets us do our on-demand rate limiting. So, for example, during the periods in the last few months where Habitat was getting pretty seriously congested, through mostly due to AutoRx, I would say, we could rate limit uploads quite significantly, which helps overloading parser. Finally, all the telemetry data is also saved to an Elasticsearch database. Currently, we aren't doing very much with the data, but the aim is to eventually create a separate tracker pointing at it instead of using the Habitat database. Total cost for all the AWS stuff is about $35 per month, most of that being Elasticsearch, which is currently storing telemetry for about 33,000 RadioSonde flights. SondHub.org also gives us a way of providing a short link to a particular RadioSonde track, be it on HabHub or APRS.5. So nowadays, when I go and recover a RadioSonde from someone's property, I'll leave my little business card with a link to the flight path so they can see exactly what happened. There's also an MQTT interface, which allows live streaming of the incoming data to other web clients. So if you want to make your own tracking app, this is a way of getting the live data coming through. We eventually plan on using this to drive a separate instance of that HabHub tracker. Also, we can do analytics on the data. So here's a very noisy plot of the altitude of all RadioSondes over the last 24 hours. So you can clearly see sondes around 0, 0, and 12 Zulu on the left and kind of halfway towards the right, along with a few at other times. In fact, one of them appears to have reached about 38 kilometers, which is a little bit unusual for a RadioSonde. We can also produce call sign plans. So here are the most prolific telemetry uploaders over the last day. Currently, the Elasticsearch DB isn't publicly available, except for a couple of APIs, but it's not very well documented. If you want to have a play with some of the data or write your own applications, come find me in the HabHub channel on IRC, or just email me. Finally, I do want to make a big apology. AutoRx has taken off, excuse the pun, and it's almost brought the Habitat database to its knees over the last few months. After about 1.5 years of RadioSonde tracking, there were upwards of 30,000 payload documents for RadioSondes in the Habitat database. This resulted in the telemetry parser to be much slower than usual. This, combined with the Habitat database cleanup operations, which kind of get kicked off regularly, resulted in some pretty serious latency in the tracker. Thanks to Adam Grigg, there is now a script which continuously removes any RadioSonde data older than 2 weeks from the Habitat database, and everything's back to normal again. We are working to transitioning away from the use of Habitat, using our own database and putting our own front end over it as well. So we should be out of the way pretty soon. pretty much it from me. If anyone has any questions, I'm not sure how long I've got, but I'm happy to take them if you have them.
Any questions, gentlemen? One at the back there?
Yeah, I just had one.
Oh, okay, Robert.
What distinguishes the radio sound from all the other junk that's around when you're searching for the radio signals? How do you pick out the radio song? How do you know it's a radio song?
Right, so what we have is a set of information on regular headers. So each radio song has a particular packet structure and a known header at the start of each transmission. So we can correlate the received signal against that header and determine whether the received signal is actually a radio song or just noise or some other signal we don't care about.
Okay, so it's a header.
Yeah, so every radio song has a unique header which is unique to that particular type of radio song. We can detect it based upon that.
Yeah, thank you.
No worries.
Any other points? Gentleman at the back there? Sorry, don't you? What's your name? Sorry.
Hi, I'm Kai. I was wondering, can you use this technology as well to track normal high altitude balloons, not just radio songs, or is that something that, you know, it could be developed into using a similar system to automatically track just normal UK hospital?
It's an interesting point. It's certainly possible. So, as an interesting relation, so on my last balloon flight, I was actually using a new data mode that I've been using over here in Australia called Chorus Binary, which is the 4FSK mode. And the modem that I'm using, which is the same FSK modem we're using in Radiosonde AutoRx, will actually find that signal in a chunk of bandwidth. Now, it's not all that good at it. The signal has to be fairly strong. So, for example, if your balloon signal is very weak, this wouldn't find it. It would probably get locked up on some other bit of noise. In short, it's a lot harder to do so. But yes, it would be possible. Someone just has to write the code.
Okay, thank you.
No worries.
Any other questions, gentlemen? Okay. Thanks very much then, Mark.
No worries.
How's the weather out there?
It's just like the UK, it's raining.
Yeah. Right. Brilliant. Okay, thanks.
Don't worry. Enjoy the rest of the day, guys.
Cheers. Okay, Michael's up next. I'm going to turn off the cameras.
It'll be fine. It's running Windows, just to be honest. The standard Imperial College setup. If it works elsewhere, probably it's going to work.
You press the button.
You want to take that one?
I think so.
You're going to excuse yourself. Can I ask you to? No, we don't need that. We're not live streaming, are we? So we've got the sound anyway.
Does it not have a signal?
It says, yeah, it doesn't have signal.
Don't worry about it.
Good. Yeah, if you can do it. You're doing very well for time, so.
I was going to say, when do you want me to stop?
11:15 is break, so you have plenty of time.
Okay. Well, good morning, everyone. Thank you very much for inviting me to talk here. So my name's Michael Johnson. I'm a bit strange for a number of reasons, but number one is I'm a part-time PhD student at Imperial, working on British spacecraft, which we'll talk about in a moment. And I'm also the founder of Pocket Spacecraft, which is a systems space exploration company. And my talk today is not really high altitude ballooning. Well, it is. It's very high altitude ballooning. So I hope you'll give me a little bit of leeway in interpretation of the topic of the conference. All right. So I'm going to use inflatable spacecraft as the hook for this, because, you know, they're basically balloons, right? So inflatable spacecraft sound like a bizarre idea, but they were actually some of the very first spacecraft that have ever flown. So NASA actually launched the Project Echo balloons, and the top is Echo 1. I'm not sure if it's Echo 1 or Echo 1A. Echo 1, unfortunately, had a launch failure and ended up in the middle of the Atlantic. So Echo 1A was the first one that made it to orbit. And that's the star at the top there. And that was basically a metallized balloon. So it's pretty massive, so 30 meter diameter, 30.5 meter diameter. And fairly hefty, so you're looking at about 180 kilograms all up. And it was fairly unusual in that it goes to a high orbit, so it's about 1,500 kilometers up, launched on a rocket, and it uses sublimation powders to actually inflate it. So, you know, no helium bottles or anything like that. And in fact, it had two different types of powder. One to do the sort of the initial inflation, basically just get as much gas in there as possible, as quickly as possible. And then a second one, which was sort of a top-up gas. So the problem is this is a fairly large object. There's a lot of little micrometeorites, small amount of particle flux in orbit. So it's constantly getting little holes and punctures in it. So it had the second powder, which was the make-up gas, to basically keep it inflated during the lifetime of this mission. So it was originally designed to be there for 3 years. In actual fact, it survived for 8, which is pretty impressive, I think. And its function mainly was to see, is this possible, but they actually used it for relaying telephone calls, TV and radio signals, just by using it as a massive red reflector. So as I understand it, they did that mainly at microwave frequencies, but I think they also had some VHF stuff as well, UHF stuff as well. And it had some trackers and things on there, probably very familiar to the sort of things you fly, so just NiCad batteries and solar cells. They did a second one in 1964, which was a bit bigger, so 40 meter diameter. This one was interesting because the first one was literally just a traditional metallized mylar balloon, essentially. But Echo 2, it was a sandwich, so they had the mylar and then aluminium on both sides, a very thin layer. And once it was inflated, they pushed it past the elastic limit of the aluminium, so it actually self-rigidized. So that way they didn't have to bother with top-up gases or anything like that. Once it was inflated and in the right shape, it held its shape. And that saves a lot of complexity. 5-year mission on that one. And one of the things that interests me is that it demonstrated solar sailing. So these things are very high, they're about 1,500 kilometers. And basically once you go above about 800 kilometers, the force of the photons from the sun pushing against an object that large, that reflective, and that light, relatively speaking, will actually start pushing it through space as a propulsion system. So it actually stayed up much longer than it would have done otherwise, just coming down naturally through the drag of the small amount of atmosphere that's up there. So I think all kinds of cool things from the Echo 1 missions. And let's not forget, that's what, 60 years ago? Pretty good going. Okay, the next inflatable spacecraft that I'm aware of, and there may well be others because the military don't really tell us too much what went on, but this one actually went to Venus. So this was the Vega mission run by the Russians, and I think that looks pretty familiar to you. Okay, and it is exactly what it looks like. So it was a weather balloon, but this time for Venus. So it was flying round about, I think it was, what was the altitude on that? I have it written down here.
54 kilometers.
54 kilometers? I obviously can't read my own stuff. 54 kilometers, thank you very much. And basically they had 2 of them. They did 2 landers which went down to the surface. As I understand it, as the landers were coming in to land, they released these things from behind the heat shields of the Vega mission, and then out they popped. And they survived quite a long time. They basically survived for 2 Earth days. So that's not bad. Of course, no GPS, so if you want to know where your weather balloon is and where you're taking the measurements from, you have to be a bit more creative. So they use something called Raylong baseline interferometry. So that's where basically you have a row of radio telescopes stretching across a 1,000-kilometer baseline, and they basically use interference techniques to figure out exactly where the thing is. And I think it's quite impressive that you can track a balloon in the clouds of Venus, which is a pretty long way away, and the thing's just flying a 4.5-watt transmitter. So, you know, where there's a will, there's a way. So I think that's pretty cool. And if you just search for the Vega mission, you can find all kinds of interesting detail. Very traditional, helium as the gas, nothing special there. Okay, now at this point I kind of say, well, thank you very much. That's the end of my presentation on inflatable spacecraft, because that is basically it. That's all that's ever flown, as far as I can tell. People have flown inflatable module. There is an inflatable module on the ISS, which is basically just an extra service module on the ISS, but I don't think that really counts for what we're interested in. However, there have been lots of proposals for weather balloons basically on Mars. Nothing's actually flown yet. There have been lots of proposals, and I'm afraid, as you'll see in a second, there are people with cooler, flashier toys who have gone first, or are about to go. But you know, the fundamental problem is, on Mars at the moment, there is a weather station. It has a temperature sensor, it has a pressure sensor, and that's it. Unfortunately, or fortunately, it's attached to the top of the MSL, the Mars rover. So we know very precisely what the weather is on Mars, as long as you want to know where it is, where the rover is. So there's no systematic study of that. So people have proposed with 8 meter mylar helium balloons, very traditional, again, nothing that's going to surprise anybody in this audience here. And if you want to give a go yourself, if you want to design a Mars weather balloon and just want to see if it works, you can get up to about 35 kilometers on Earth. You're in Mars atmosphere. It's a very good analog in terms of pressure, temperatures, and all that kind of stuff, which is quite nice for prototyping, as we'll see later on. Of course, with all these things, are you going to fly a battery? Well, if you are, you probably have to survive a year's worth of cruise as you get from Earth to Mars. So how practical is that? So you probably want it to be solar powered. If it is solar powered, the amount of sunlight per square meter is about a quarter of that on Mars as it is on Earth. So your solar arrays have to get bigger. So you'll need to worry about that. And as I say, there are these competitors. Rovers and a Mars helicopter, which sounds very cool. Studies that have been done, basically there are 2 contenders, and as far as I can see, they kind of died a death because of the flashier stuff. So this is the Mars 2020 Mars helicopter. This is basically being prepared for launch at the moment, and that will carry, it's designed really for reconnaissance from the rover, so you can have a look for places that the rover can't get. So launch from the rover, flies off, comes back again. But you can imagine carrying weather data and that kind of stuff. That's a JPL project, and that should be launched, I think it's March next year, something like that. Okay, so that's the end of the inflatable spacecraft bit. The other thing I do is system and space exploration. So at the moment, most people doing space exploration are space agencies. It's sort of hundreds of millions to billions of dollars per mission. Even if you spend that kind of money, there's no guarantee of success. Only about 50% of them succeed, or those missions succeed. So I thought, why don't we try and find a way of sending a spacecraft to everybody in the solar system, basically before I retire. And that was 8 years ago. I've got 17 years left, so let's see how we get on. So the first thing is, what do you mean by everybody in the solar system? So there's a lot of wriggle room here. If you're looking at big things, so things with a radius more than 5,000 kilometers, there are only 10 places you have to go. But actually, if you look at stuff that's more than half a kilometer or more, that's 1 million objects. And to me, that's the interesting problem. How do you send 1 million spacecraft around the universe, or around the solar system at least? Because it's clearly not going to happen with $1 billion a mission, and with control rooms full of people with headsets, times 1 million. It simply isn't going to work. So we need a completely different approach. So the idea I came up with was the idea of pocket spacecraft. So this is the spacecraft that any private individual can afford to buy, launch and operate with little or no technical expertise. And by doing that, let's see if we can kick off the age of personal space exploration. So obviously there are things like Arduinos and Raspberry Pis, so the expertise is actually out there. If you want to code stuff, you can give people a useful platform. The question is, will anybody actually let you do this or not? Luckily, the answer is yes. So in 2012, we did a Kickstarter, and this was a mission called KickSat. And we basically said, there's a very low-cost type of spacecraft called a CubeSat, which is something called a 3U CubeSat, is 30 centimeters by 10 by 10. And basically, you can get these things launched for free if you can make a good enough case to NASA, ESA, one of the space agencies. So we went out to Kickstarter and said, if you paid either $300 or $1,000 for your own spacecraft, and the difference was for $300 we would transmit your initials from space, and for $1,000 you'd be able to upload your own code to run in space, would you be willing to back that kind of mission? And luckily 315 people said yes. We raised about $75,000, which isn't a vast amount of money in the realms of space exploration, but it was enough to actually launch this mission. So this 3U CubeSat was loaded with 104 of these very small spacecraft. And the advantage of working at this scale is you can carry them in your pocket. So that is the spacecraft that launched, 104 of those. And it seems to me that's pretty close to what you want to have on a high altitude balloon. So you have self-contained 120 milliwatts of solar power. There's a radio transceiver operating amateur radio frequencies, magnetometer, gyroscope, accelerometer, temperature sensors. It's pretty much all there. Now this is a development one, so it's got an extra programming block and an SMA connection for debugging. The real thing is just this PCB with all those components, and then a couple of memory metal antennas, and that comes in at 4 grams. So I'll just pass that round. Please be careful with it, and I need it back at the end. That's okay. So this was actually launched in 2014. Unfortunately, there was a failure for the actual deployment, so the CubeSat was launched on the Falcon 9 rocket, which was what you saw take off in the corner there. But unfortunately, the CubeSat, the small spacecraft weren't actually deployed because there was a lot of traffic around the ISS at the time. So when the CubeSat was deployed from the rocket, it had to run a 15-day counter before it was allowed to actually release all the smaller spacecraft. Now, unfortunately, on day about 14, the cosmic ray reset the counter, and it started its countdown on April 15. So normally that would have been fine, but because people are worried about space debris and things like this, this was in a very low orbit, so that both the CubeSat and the small Sprite spacecraft would re-enter as quickly as possible, not to cause any damage. So on day 14, I think it reset the 15 countdown, and on day 28, it re-entered and burnt up, when of course it would have deployed at day 29. Very frustrating. Such is the way of space, however, and you get a reflight and you just go again. So in 2019, earlier this year, it was launched back up to the ISS, hadn't been rebuilt. It was deployed and it actually worked this time. So finally, a mere 7 years from concept to execution, we proved that systems space exploration is possible for $300 for your own spacecraft. Cool. All right. However, I think you'll agree, if you want to do this at scale, particularly with millions of customers hopefully paying for this, a 7-year wait from credit card payment to satisfaction is unlikely to be terribly friendly. So while all that was going on, we were looking at how do we sort of reduce the cost of this further, and how do we improve the sort of scientific viability of these things. So the first thing is that 4-gram spacecraft, 104 of those into a CubeSat, that's great. The cost of launching a CubeSat is sort of between $50,000 and $150,000, depending on who you go to. Divide it by 100, it's pretty good, but it's still not cheap enough to give these things away in cornflakes boxes, which is what I'd like to do. So the first thing is, how do you reduce the mass? So basically we went to Kapton, stripped out the raw dye from the chips, and we printed as much of the passive electronics as possible. Now this one's just a printed model, this isn't the real thing, I'm afraid. The real thing is much floppier, and you would definitely tear it by the time it got to the back of the room. So I'll pass this round, it's essentially a picture, but you can have a look and see. But the nice thing about this is you can now get 1,000 per CubeSat, so that drops the cost of the launch element by a factor of 10, which makes it far more reasonable. The other thing is it's very customizable, so it's based on printed electronics. And that means that we can sort of design a programming language to say, I want a mission that collects this information, this data, and have a whole bunch of software tools that will actually configure a spacecraft for you, which we'll talk about later. To do that, we use basically in the lab-based inkjet printers. You can get inkjet printers that print conductive electronics, resistors, dielectrics, and capacitors, even semiconductors, although the transistors are quite big and not very reliable. So basically, we've been spending the last few years just proving that all this stuff works, building, in this case, for example, a spacecraft with a micrometeorite detector, putting it into something called a light gas gun, which is where you fire particles at a few kilometers a second and just check that it doesn't destroy your entire spacecraft, and basically just proves that the whole concept works. And if you go back to the solar sailing of those big balloons, solar sailing works because it's all about the ratio of the mass to the surface area. So I don't know how big your balloon payloads are. I'm guessing sort of 500 grams, a kilogram or so. Is that about right? Okay, so if you just scale everything down, our payloads are of the order of 2.5 milligrams. That's the cost, that's the weight of the silicon die and the passives to support them. And if you add on the rest of the Kapton and the silverization and some of the solar materials, you get up to the order of sort of 1 to 200 milligrams, depending on what we're doing. And that means we can solar sail. So that means if we get above that 800 kilometers, we put on special materials, basically liquid crystal shutters like on your black and white LCD watch, change the reflectivity of the spacecraft, and at that point we can steer it and actually start going around the solar system. Okay, so yeah, I mean, this is basically just saying turning things into software-defined spacecraft. So we have SDRs have revolutionized how you do radio stuff. Well, we want to try and do software-defined spacecraft and do the same thing. So we have a programming language for actually defining what you want to collect and all those other bits and pieces. So as of 2017, we were able to basically do this. So you start off at the top left with what's called a traceability matrix. So this is how scientists say, I want to know what the weather is on Mars with this level of precision. And then we have a tool chain that will derive automatically what properties a spacecraft has to be able to collect that information, work out the trajectories to get it to the right place so it can actually do that, and then control the processes in the lab to actually manufacture these spacecraft. Now with this approach, it's the traditional way of doing things. You still have to find someone going to Mars or wherever. You have to attach the printed spacecraft to that, and then, for example, maybe they're dropped out as breadcrumbs behind a rover as it goes along. So it's great, but we've still got that sort of decade-long process in the whole thing. What I'm working on at Imperial is actually trying to get rid of that decade. And we do that by actually moving to the thing that's been deleted off that slide. Okay, so in this blank space here is a spacecraft printer. I have no idea why that's disappeared, but okay. And the idea there is that instead of having the printers in the lab, if you have them in orbit around Mars or attached to the back of your rover or whatever, you can get rid of that decade-long delay. Now you still have the delay to get that printer to where it is you want to go, but once it's there, it's designed on your computer, speed of light delay, sort of 40 minutes to Mars, worst case, an hour or so to manufacture the thing, and out pops a new mission. And that means we can do new missions in hours instead of decades. Now that's great at places like Mars, although the delay there is not that bad. Realistically, there's a chance every 2 years to send stuff to Mars. But if you're going to outer planets, if you're going, say, somewhere like Europa, looking for life, you know, it's realistically taking 20 or 30 years to get the first missions to go there. We've never sent a high-resolution imager anywhere near the surface. That's basically being prepared now. It will arrive probably in about 10 years' time. If we see something interesting with the current system, we now have to wait 20 or 30 years to go back and have a look and see what was the interesting thing we saw. With this kind of system, the idea is that we actually react to what we find. We print the instruments we need to do that. And I'm very sorry about that missing thing because it's a really cool picture, but it's not there. Okay, so how far through are we with this mad scheme? Pretty much. All the software is done. We've done a couple of proof of concept missions, so a deep weather space weather buoy, so that's basically flying spacecraft out in the solar system, looking at the solar wind, looking for coronal mass ejections, things like that. The little thin film thing I passed around, that's actually a Mars weather station, so you see it's sort of quad. There are 4 systems repeated, so it's a quad redundant weather station, so essentially a weather balloon, but designed to be dropped as a breadcrumb behind a rover. And we're just in the process of getting all the licenses out of the way so that we actually go and fly one of these things for real. Oh yes, so that's the weather station. It's got to run on 200 milliwatts, so it doesn't have a huge amount of power to work with, and that's a lot to do with the reduced solar flux on Mars. Pretty much the same as that KickSat spacecraft, so but with the addition of humidity, pressure, and pressure sensors. One of the big topics people are looking for on Mars are there dust levels. No one really understands what are the surface conditions that cause those dust levels to happen. So this mission is being designed, the spacecraft's been designed to handle that. It turns out everything in space pretty much is compatible. So these standards called CCSDS standards. So we've made sure that the spacecraft we design are compatible with the infrastructure. because that way you don't have to return the data directly to Earth. As long as you can get it to an orbiter nearby, whether it's Russian, American, Chinese, or whatever, everything's compatible. So these are the cream of 1980 data standards, but it doesn't matter because everything supports them. So it's really good. And if you want to know how to get the highest possible data rates with the lowest amount of power, all these standards are open, and I strongly advise you to have a look and get some good ideas. All the really good comments in them. And another thing we worry about is we have to, for a Mars mission, make sure it's compliant with the Coast Guard Class 4C planetary protection rules. What are those? Well, we're not allowed to infect Mars. Any spacecraft that goes to Mars, or anybody with any realistic prospect of there being life there, it has to be sterilized. So we have to design these balloons, we have to design these spacecraft so that they can survive the very fancy sounding dry heat microbial reduction technique, which basically means stick it in an oven for 125 degrees for 48 hours. So as long as your electronics and your device can survive that, then you're good to go to Mars. So you have to be a bit careful about choosing epoxies and conformal coatings and things like that. That's doable. Okay, how do you communicate with these things? So realistically, these things are about 10 milliwatts. So what you do is you borrow a 1,000-kilometre wide radio telescope to do that. So for example, this is something called a LOFAR. So if you look at the top right, those blue things, they're not actually solar cells. They are 128 omnidirectional VHF antennas under a cover to stop the rain, keep rain off them. And it's a phased array system. So it's basically entire software-based radio system. 128 antennas. There are a dozen of those sites spread around Europe, so you get about 1,000-kilometre baseline. And that means that I think in total there are of the order of 10,000 individual antennas with a supercomputer in the middle. Now that gives you two things. You can do navigation, so you can look at the delays. So if you pick up the same signal here, here, and here, you can look at the different amount of time it takes for the signal to get to you, or the changing phase, and through triangulation work out exactly where on the planet your spacecraft is. But more importantly, because it's a phased array system and it's essentially all software, so you've got 10,000 RF streams coming in simultaneously, you can track thousands or potentially even millions of spacecraft simultaneously because it's just software. So we did an experiment with this back in 2013 using a payload attached to a Chinese rocket that did a lunar flyby, and that proved that we can actually, this sort of system works. And amazingly, if you send an email to the director of the radio telescope observatory that owns this and say, please can I borrow your radio telescope to do an experiment with a Chinese spacecraft, they go, yeah, sure. Now, I was expecting it a lot harder to get that negotiation, but fine, whatever. Good to know, I think. By the way, this stuff is compatible with the frequencies used by your weather balloons, so you might want to try and borrow it yourself for some interesting ideas. Okay, so what do we want to do? So lots of spacecraft to the moon. That's a mission that we've currently built. It's launch delayed, sitting waiting for the rocket to take off. That'll be basically a little over 1,000 people trying to do a lunar flyby, and a lunar impactor, which is the polite way of not a soft landing. I think the Indians did one of those last night, accidentally. Looking up at doing missions to interesting places like Saturn, sort of search for life stuff is what's really interesting in this field. But the reason I'm here is that I'd like to try and do some inflatable versions of these for Mars. So you can imagine if we take those little things, I've done the maths very, very roughly, and I will say my numbers are good to an order of magnitude-ish. So by my calculations, I reckon a 10-centimetre inflated Kapton thing, like the thing I pass around, with a 100-milligram payload would allow us to float around Mars and do some weather balloon typey stuff. And now we can try that at 35 kilometres if it's even maybe possible. So if anyone's interested in having a go and like a collaboration with me and Imperial, let me know, see me after the talk, and we'll have a think about it. So anyway, just food for thought. I'd like to thank the funders, because none of this stuff is possible without funding. First of all, more than 4,000 private individuals who have funded various bits of these projects, space agencies, the funding agencies, and the universities who let us play with these crazy ideas. And that is me. Thank you. you very much. Any questions? Yes.
You mentioned the citizen science app. Can we buy them to play around? Or?
Yes, and everything's open source. So one of the nice things about doing space exploration, well, one of the bad things about space exploration is that they're regulated exactly the same way as machine guns. So if I build a spacecraft and I hand it around the room like this, if it's closed sourced, we all go to jail. However, as long as it's in the public domain, for some reason available by second-class mail or presented at a scientific conference, it's completely legal to make these things, share them around and export them. So yeah, by default, everything's public domain. And we provided development kits. One element of the Kickstarter was the people who backed the spacecraft got a version of the spacecraft themselves to play with it. So yeah, everything's open. It has to be. Yes?
You've already mentioned that cosmic rays knocked out the timer on the CubeSat.
Yep.
These disks and these little things look so small that surely they're going to get hit by cosmic rays.
Yes, so there are a number of ways you mitigate that. So first of all, you design it so that the things can survive that happening. So for example, they're constantly looking for corruption in the memory. The timer that was upset was an off-the-shelf watchdog timer, whereas with these things they're actually designed with special operating systems looking for corruption and fixing it as it goes along. The second thing is for the printed devices, the actual transistors, the printing technology is very bad, so the individual transistors are about 1 millimeter square, but that's good because they're very robust and resilient to cosmic ray events. So it actually kind of worked in your favour that they're such crappy transistors. So. Yes?
How do you deploy out the CubeSat?
So it's a very technical, electromechanical deployment system which we call a jack-in-the-box. So basically it's a box with a lid, a big pusher spring behind. Everything's in compression, so when you launch the things, the launch forces don't shake everything big to pieces. And once you're in the right place, you have a burn wire, which is literally a piece of fishing wire holding down a spring-loaded lid that opens, and then there's another big spring that physically just pushes these things out. But it's very complicated space engineering. You wouldn't understand it, so I couldn't possibly tell you any more details. Yes?
These film weather stations that you're planning on dropping out to the back of a Mars rover, you're saying you're receiving them with these phased array antennas all across Earth. Is there any directionality to the transmission, or is it literally just 10 milliwatts and you've got a big enough telescope you can just see it?
Exactly, 10 milliwatts omnidirectional. And actually one of the nice things is the square kilometre array is about to come online. So that makes LOFAR, which is the one we use there, look like a sort of a kid's instrument. So yeah. The fundamental calculation is it's always cheaper to buy or borrow stuff on Earth than it is to have high amounts of power in space. So yeah. Sorry.
You mentioned the possibility of us helping out with flying stuff up. How well formed is that? Is that something for this year, next year, the year after?
I will admit it is a slide I put together last night, thinking what would be of interest to the people sitting in the audience. But why not? Yeah. I mean, the conditions are well understood. It's a cool, fundable project. It's not going to fly probably for 4 to 6 years if we make it work. But if it does, there are constant opportunities, and I think it's very viable. We should get it launched and give it a go. As I say, we're competing with a single sensor attached to a single rover that is already operating past its lifetime. So I think it's worth it. Yeah.
I mean, for us here now, and from my perspective with schools, testing something that might go to Mars has a big hook.
Yeah.
How soon are you going to be ready, us, to put something on our payload?
So it depends what we want to do. So if you want me to build everything and you're basically taking it out there and dropping it, that's probably something that could be done by, say, spring next year. But what I'm really hoping is that we have a collaboration actually developing the small balloons themselves. Okay, so essentially I'm a physicist and pretending to be an aerospace engineer, so I know how to build the thin film spacecraft and all that kind of stuff. I'll be frank, I know nothing about high altitude ballooning. This is all you do. Well, it's not, but you know what I mean. So, you know, why reinvent the wheel? I'd far rather learn from your experiences and everything else. So I'd like to develop both together as part of the amateur community. But, you know, it's what people are interested in. So.
I mean, you can stick one on those on a foil balloon today. You know.
Yeah, exactly.
Yeah. We've even got some.
Yeah.
But, you know,
well, no, to me it's the inflatable aspect. So the thing that makes it useful on Mars is the fact that you can imagine having a little box on the back of the rover where basically you inflate one, detach it, wait for the next Mars day, inflate one, detach it, and then they blow around. So that's going to be operating at unusual pressures and temperatures compared to what you're doing. Now we have space simulators where you can simulate those things in the lab to sort of actually work with electronics and all that kind of stuff. But there's nothing like doing it for real at the right pressures to actually see all the things you forgot. So, yeah.
you can save some of the gas from the balloon, cook it up.
Yeah, exactly.
Smaller balloon.
Yeah. Sorry, there was a question.
I wanted to go back to your Jack-in-the-Box launch technology.
Yes.
That sounds impressive, but to me it seems like it's a path popper going on, so that you've got all your microsatellites in one piece of space, shall we say, very close to each other. Is there any way of, let's say, launching one an hour, one a day, one every 2 hours, I don't know, so that they're in different pieces of space? I know that if you launch one and then 2 hours later they're not going to drift far apart, which I'm thinking perhaps one a day.
Well, there are a couple of ways of handling that. So I was talking about the solar sailing, and we have these things called reflectivity control devices. So if you change how reflective each of the spacecraft are, either permanently by essentially having a different percentage of area of reflectivity on the surface of each one before you launch them, or with active devices where you can change the reflectivity in situ, then even though you're launching them as a lump, you can get them to spread out and to actually physically go different places. You know, you can actually do things like orbit raising. So if you go high enough, so 800 kilometers at the bottom, if you start off with everything there, you can go to Mars or Venus or whatever from that starting point. It's not going to be fast. It's going to take you sort of 10 years or so to do it, but you can get that level of control and separation of these devices. We have looked at sort of having essentially imagine a pile of these things on a thread, and as you turn the thread, it pops them off one at a time. It does work. It's not hugely reliable, and there is scope for releasing either one at a time or lumps of 10 or 20 at a time. It's a sort of risk-reward trade-off. The nice things about Jack-in-the-Boxes is that they're toppler-proof, and therefore they will work once they've been launched and shaken. And so it's really what's more important to you? Is it that temporal deployment, or is it knowing they are all going to be deployed and then spread them out after that's happened? So it's kind of an open question, but I am at the crazy end of the aerospace engineering spectrum for this stuff, right? So everything else has to look as conservative as possible to get the chance to fly. So that's the tension I have to do. Yes, I'll go right to the back.
Presumably you can tack these things and sail into the wind in the same way that you can do with a conventional wind sail.
Yes, I mean it's not exactly the same principle, but yes, that's the whole point. You can go anywhere, so you can get close to the sun and you can go far away. Yep.
I was just wondering, how much of this can you print at the moment? Is most of it printed, or do you still have to add a lot of layers on?
So it's all about performance. So I can do an entirely printed spacecraft, but it's got about 150 functioning transistors. So that's not quite as dire as it sounds, but it is still pretty dire. You're kind of at sort of the very first digital computers that were ever created. For things where you're actually trying to demonstrate stuff like the solar sailing and stuff, you need a bit of compute performance on there. So the trade-off there is we bond fairly high performance die with the radio and the compute on board, and then all the instruments basically, if you're going to use this stuff for real science, that's where it will stay for the next 5 years or so. But the end point is to get to fully printed devices with high performance. And we actually do have another project working on trying to get sort of tens of thousands of transistors manufactured and printed. So that's where we are today. Version 1. Yes?
You're saying these discs are flimsier than this example you just showed us?
Yes.
So mechanically, are we going to have a high attrition rate of space dust like a meteorite hitting them?
Yep, but luckily they're really cheap. So they're about $20 a piece. So if you think of a piece of cling film, that's the sort of texture and mechanical properties. So we put a hoop of memory metal around the outside, which the Kapton is basically draped over and bonded to. So that holds the shape. So that. But yeah, they're fragile. But the point is, it's far cheaper to build 10,000 individually unreliable things, but together they're incredibly reliable, because all 10,000 of them have to die, or maybe 5,000 of them have to die to compromise your mission, as to building one thing for $1 billion that absolutely has to work. The reason it costs $1 billion is not because there's $1 billion worth of parts in there, it's because there's about $990 million worth of testing and QA that goes into it. And I know that sounds stupid, but that really is the ratio. So
you're going to print the electronics onto the disk?
Yes.
In situ on Mars?
Okay, so that's the. So we have a couple of different projects going in parallel here. So the discs you have, we print those in the lab, but the end goal is to print the spacecraft. We probably wouldn't do the balloons on Mars. These would be printed in space in orbit. So this is something we hope to demonstrate next year. So we're building a CubeSat that will actually demonstrate this. And it's quite small, so it's limited to 50 millimeter by 50 millimeter spacecraft. There's kind of a continuous Kapton substrate that just appears. It's like a 3D printer. Have you seen the 3D printers with the Kapton conveyor belts? Okay, so you can imagine. So you can print thermoplastics, so you can do 3D structures. We can bond modules onto it, and we can print conductive electronics, dielectrics, and resistors. So it'll be very, very crude, the first ones. But yes, the end point is to manufacture these things in situ.
And that's better than prefabricating on Earth and then you just stack in the lab or disperse it?
It's all about time. So if I want to do this at Europa, it will always be more reliable to do that on Earth, but it'll take me 30 years when I find something interesting to prefabricate my stuff on Earth, get it approved, get it funded, launched, physically get there, and then take the measurement. So my argument is you're better off having something, even if it's crude, getting some data, than waiting for those 30 years. And I'm pretty certain the combined ingenuity of people who do Arduino and Raspberry Pis and all that kind of stuff over 30 years beats the space age engineers doing it the traditional way. I could be wrong, but that's part of the fun of finding out. It's a trade-off. Do you have lots of dumb things, unreliable dumb things, but there are lots of them, so at least some of them will work, versus one exquisitely engineered thing. And I think IoT and stuff has sort of shown that it's probably the unreliable lots of things man that will win in the end. But I could be wrong. But it's fun trying to find out.
Oh, sorry. Well, just one more question then, I think.
Okay.
How resistant are those things against temperature changes?
So you design them to be resistant against temperature. So the thin film devices in orbit, they are designed for low Earth orbit, which actually isn't that challenging. As long as you can survive traditional industrial electronics temperature ranges, minus 40 C to plus 80, you're good to go. Somewhere like Venus is a lot more challenging. The clouds of sulfuric acid don't help. High pressures, blah, 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 blah. You choose the right electronic processes to survive that. In fact, nothing to do with this project. If you want to see a really cool approach for surviving hostile environments, have a look at the JPL Clockwork rover for Venus. That is an entirely clockwork rover, even down to the data transmission and the camera. So basically you have to choose the materials to be compatible with where you're going. And also lifetimes are different. You're trading off lifetimes a lot as well. So to survive on a lunar crater in shadow for more than a few hours, you're doing well. Even the billion-dollar missions to, say, Europa, they will have lifetimes measured in hours because they're pretty much going down to 4 Kelvin, and you just cannot thermally insulate these things and keep them warm, so they will die eventually. So it's a compromise.
Okay, thank you very much, Michael. We've now got about a 20-minute break, so teas and coffees all round. Coming back at 11:35.
Good morning. So I'm Dave Acorn. This is about my Apollo 11 flight, which was basically to commemorate the moon landing back when I was this big and wasn't sure what was going on. I thought I should fly something, and then a guy from Vice Behind magazine emailed me and said, Dave, you're doing anything for Apollo? We're doing a special in the magazine. So we had a chat and agreed to do something. And then he didn't turn up, but anyway, it was a good flight anyway. So the plan was to fly something. We've all done the teddy bears and plastic toys and everything else, but something a bit special, hopefully. So I remember this from when I was, I think I remember watching it live at 4 in the morning, I'm not quite sure. But anyway, so I looked around and found this kit, which Revell do. They did back in the day, and they've re-released it this year because of the anniversary. And it was about 15 quid, so I ordered that. That's good. And it came with all this stuff, which reminded me about using Airfix kits when I was a kid. Back when glue was for gluing things instead of sniffing. And lots of little bits like this. I'm not sure why they gave me an astronaut to put inside the capsule, which you can't see when you built it. But I think the idea is you can build it in different configurations. And I did look at what configuration would the spacecraft have been above the Earth. And the answer is all hidden inside the rocket, basically. But on Apollo 9, I think it was, they did the docking maneuver in orbit around the Earth. So you would, if NASA had bothered putting another spacecraft up to video it, they'd have had what I've captured in this flight. Anyway, there's a lot of painting. I discovered my eyes, which have got basically a focal length from here to here, are good for something, which is painting little models. So it took quite a while. That's the capsule, which they came back down in. Looks quite nice. All of those little windows, they give you little bits of plastic to put in them. I mean, I went the whole 10 yards and built all of it, but you wouldn't really notice. And that's the service module, and you've even got microwave dishes on the end. So it's quite a detailed little kit. And then you've got the landing stage and the lunar module. That's the glue. And then this bit. And you don't have to do the whole lot together, but I did. So I made that, which is, and it's been up into near space now. I put a lot of thought into it. I mean, when I made it, that's actually not quite straight, so I oriented it that way with the camera here, so that all the parts would be roughly the same length from the lens, and there was quite a lot of thought behind it. There's one of those in the Science Museum, and I had a look a few weeks ago, and it's not built as well as this one, actually.
And it hasn't been to space.
And it hasn't been to space, perfect.
Or near space.
No.
Near space.
I stood there photographing and wanted to tell everyone, I've got one of those. It's worth mentioning this bit here, that's carbon fibre rod, 2mm thick. And again, if you can't really quite tell, there's a bit of plastic just behind it. So the idea, the camera was this end, so that join there was hidden behind the top of the curve of the capsule. So just, I had plenty of time to figure this stuff out.
Too much time.
Too much time, possibly. So having built that with the vague idea of putting camera in front of it and flying it, and that was weeks before the flight, so what else can I do? So I remembered this, and I'd love to have been working in there apart from you wouldn't see anything because of the cigarette smoke, and I'd have cancer by now. But apart from that, I'd have loved to have been involved in all this stuff. So I don't know if anyone remembers my Telnet flight, which I talked about last year, I think, and I did a mission control emulation then. So I basically took the same thing and then stretched it a bit, removed the rounded corners because they looked a bit rubbish when we put video inside, and built this. So that one there has got, this is a YouTube feed into the middle. These are buttons, they're a bit crummy, but I ran out of time on that one. And this is actual telemetry from the flight. Yeah, that's a cheat actually, I think, because that's not the altitude there. But anyway, that's live. That would be live telemetry. I'm not sure why. Oh, maybe I played that back or something. I'm not sure. Probably. Oh yeah. So first off, that's all black and white. So how do you do black and white streaming to YouTube? So what I have is a Raspberry Pi Zero and a wide-angle camera, and then this little script that gets automatically started. And this bit here is what makes it black and white. So you set the colour saturation to 0, and then FFmpeg streams to YouTube on that channel, and it just gets filled in when the script gets started. So then you stream in black and white. And I spent more time making this thing in black and white than any other particular aspect of it. That's the SSDV, but this is faked because SSDV, I just used the regular page that Phil produces. For this, I just cut and pasted a picture from the SD card after the flight. But, so it looks a bit better than it really did. And that's, I launched it from Ross on Wye in Herefordshire. That's the 7S3 crystal channel down there. And again, the SSDV is in black and white, so how does that work? You just, this is a Pi in the Sky I ran, and that's, you just set camera settings to that. So that tells Raspberry Still, which is the Pi still picture program, those settings, and that makes that work in black and white as well. Oh yeah, so the data, this telemetry up here, I could have just got it from HabHub, so I could have just had the script, get data from there, or Space Near is a bit quicker, but anyway. What I did was I've got my own server, so this is like a toy version of what DarkSide was talking about earlier for the radio songs. This is running on AWS. It's basically a Linux machine in the internet somewhere. It cost me about $1 a month or something like that. And I wrote that for another flight, which I've still not done, which is basically where Phil and I are going to have a chat via 2 balloons. So he's going to sit in Northern Ireland, type "Hello Dave," he's going to go up to the first balloon, echo to the second, handshakes and retries and all that jazz, and then down to me. And what I want to do is have a dashboard that shows all those messages bouncing around in real time. And there's no way I could do that with HabHub, because it doesn't respond quickly enough. So the idea is I've got my own server here, all the telemetry, including those key types, key presses, is sent from the gateway. So those of you who helped track this flight, where you did enable havlink equals yes, you were just enabling that, and that's a socket connection from your gateway up to the server. So all the telemetry you received went up there, and also some metadata, but don't worry, it's only your IP address and your call sign. That was it. And then that gets fed down to the dashboard here, has a WebSocket, so that's basically, it's like a socket but over HTTP, and all of the telemetry for selected flight. So when this starts up, it sends a message up here saying to the server, I'm interested in the flight called Apollo, or the list of payloads that it's interested in. And then every time there's a new message from the balloon, that gets up there. And also there may be 7 listeners, so they get it just use it once, and then send it down straight away. So basically the delay between telemetry being received from the balloon and appearing on the dashboard is way less than a second. That's how that works.
Less than 30 minutes.
Less than, Yes. The other reason I used this is because that was when HabHub was 30 minutes behind on a flight, which was just, it was useless basically. Anyway, that's all fixed. If anyone's interested, that's written in C. This is written in Delphi, which is Object Pascal, which is just the thing I use commercially mostly, so I'm familiar with it. And the nice thing is it's cross-platform, so you can write for Android, Mac, PC, iPads, and Linux command line programs. And now you can do graphics on that as well. So that's just Delphi program receiving the data. And this is weird. The dashboard is written in Delphi as well, and it's cross-compiled from Delphi into JavaScript. So when you load up that page, you get a load of HTML, bits, CSS, and a load of JavaScript comes down to your browser to run all that stuff there. So I know no JavaScript, and I'll show you some in a minute. I don't understand it, but because I did Delphi all the way through. So that's how that worked. And so yes, all this data here gets filled in from that feed. This is a Google map. It's not Space Near Us. It's just a Google map using my API key, and that position is filled in from the telemetry. So it's not reliant on Space Near for the same reason as earlier. Next. And the reason that's in grey, and you can make Space Near Us in grey exactly the same way, because I've tried it. And you just set this style, you just set grey to grayscale, and it makes everything in that window there grayscale. So I didn't want anything in colour that was in that area, because they had, NASA just had grayscale displays. The next screen there is 3D. So what I had to play with a while ago was doing like a Google Earth live during the flight and embed it in a window here. And when I searched for that, I found a thing called Cesium. It just says Cesium there, just about, which is an online map where you just write some JavaScript in your browser, and then you load up a window, and then you can set where it is, you can set all sorts of parameters, and live feed, and that's the view from a flight. One of Steve's flights that he kindly gave me the NMEA for a while back. So all I'm doing there is, every few seconds, it updates the position from the playback telemetry for Steve's flight, and it just gently rotates it 360 degrees.
So it goes right through to landing, does it?
Yeah, I've done it from, it looks a bit, yeah. On here you've got all these, you've got controls as well, and you can mess around, but in the code, and that's the only JavaScript you need to load a window like that. So most of that is turning off all the clutter on the screen I didn't want. So mode pickers and full screen button, so it just turns all that off. And the only thing that's left is the Cesium logo. I don't think you can turn that off, unless you pay for it, and I didn't do that. And I wanted that in black and white as well. You see the video just now was in colour. So I thought, okay, it's going to be called grayscale, and I may have misspelled grey that American way. It's called mono. No, it's called black and white. So that took a while to find. But basically, you just set this post-processing thing. All that, I believe, happens on the server. I'm not sure exactly, but you just set this thing, and then you get really blocky, I think it's 4, 5, 6 levels of grey, and then you have to find this magic, which is set it to 256 grayscales, and then you get a grayscale version of the colour rendering. So that window there, that code there just creates it, and then the second bit here, there's a routine called fly-to. So this is written, it looks a bit clunky, that's in Delphi, and that's just converting degrees to radians. And then this bit here, ASM, traditionally with Delphi, when if you wanted to write assembly language, which back in the days you did, you just bracketed it with ASM and end. and they've used the same idea to embed JavaScript. So that's direct JavaScript in the Delphi wrapper, if you like. So I do this, and I've got a module which has got all the teasing routines that I use, which is only 2 or 3. So the rest of the program's in Delphi, that's in Delphi, and then just that bit is setting longitude, latitude, altitude, and then you can set heading, pitch, and roll. And if you're sensible, and I did try, but you only really want to do the heading, you don't want to do this stuff, which is what wheel balloons do, but then the viewer might need to go to the bathroom. So next screen there, telemetry. So this is, I ran 3 trackers during the flight, 2 at landing prediction, which Steve and I are going to talk about next. And that's the basic telemetry for each one. And that's the latest telemetry received from any of the listeners that were listening at the time. That's that one. The stats screen, I didn't realise how many receivers, and it scrolled off the bottom and then looked rubbish. But I did have to. There was a bug or 2 in the server, and I had to reset it a couple of times. So I think this will have to reset. So these are the listeners. So this information came in the metadata that got sent from your gateways, and then how many of each tracker that you received at that point. Yes, that's it. So that wasn't enough. So I thought, the consoles, how more retro can I get? So I added in this stuff. Okay, that's it. Yeah, actually, can we get sound? There were Quindar tones as well on this stuff. So that interference kind of, not locked to, not synchronized to the signal. That was just a GIF that I just stretched over the top. So when you press the button, it turned the GIF on for a couple of seconds and then turned it off again. Let's play that again. And then SSDB page. And then I have that YouTube, until I set my streaming up, I just use that. Cool. Right, so the flight itself, I wanted to launch on the launch day for Apollo, but the wind was rubbish and that didn't work out. So I think this was on landing day then. So that was the prediction, and I love these. So when your prediction basically goes back over where you launched, all you need to do is set the burst altitude so that it goes here instead of over here or over here. So I chose the right size balloon. It's handy if you, Steve's got 10 times as many balloons as I have, but I try and keep one of each size in stock. So on the morning of the launch, I can choose the right size balloon to get exactly what I want. And it actually landed just a bit further up. So this was for a certain time in the morning, but I launched a few hours later, because very usefully, someone, I won't name names, launched a balloon in the morning on the same frequency as one of my trackers. So I used the excuse to delay, but actually it was handy. It was stress-free if I just delayed things a few hours. And then the payload was a Pi and Pi in the sky. I used a wide-angle Pi camera because when you've got something this close, you need a wide-angle lens to get it in. It was either that or a regular one and have it out there, which is possible. I used an SJ4000 video camera because I did a test between that and some GoPros and some other cameras I had, and that was the one that was best for close focus. So action cameras, some of them are designed for, when you jump off cliffs and things and do all that sort of stupid sports, where it looks at your face and it gets nice and sharp. And the SJ was good for that. The problem is, focusing close, as like me now, I can't see you lot. So the Pi camera is a bit of a compromise between close focus and distance focus. And then I flew an AVR tracker to back up as well. So that's the payload there. That was a last minute bit of tape because the top of that waterwood was in view of the camera at that point. And that's it there, pretty straightforward. Lots of pink tape. even Steve's got them pink, haven't we, now? That's the AVR backup. I like flying those because you put the battery in and it works. You don't have to worry about anything else, like SD cards not plugged in or not booting or anything. Okay, right. So I was jumping ahead a little bit really, but this is a fairly hilly area. So I drove around the roads nearby and I found a place that was high enough that I hoped I would still get signal when it landed, which I did. And then try to figure out a way of getting from the road to where the payload was. And there was a track, but I didn't know who owned it, so I asked a local who sent me to the offices for the people that owned all the land. And they very usefully printed me out of sheets with all the public footpaths. And that's the payload there. That's a public footpath all the way down to the road, and their offices were here. And I was earlier. Here somewhere. I could have got actually most of the way up there in my car if they'd said it's okay to drive your 4x4 up the track, but they didn't. So I had a fairly steep walk up that way. I didn't get the signal until I was about here because of the hills. So and to track, all I had was a phone with got LoRa receiver, which is basically a LoRa module and an Arduino with a USB interface on it, plugged into the phone, and that's it. I just carry that. Yeah, there we are. I was quite pleased. And amazingly, I mean, you can see in the grass there is quite long. That piece of balsa broke off the payload. It must have hit. This must have hit the ground first, but it's still in one piece. And you look at those legs. I mean, that one's bent from where I broke it before, so I was quite pleased it didn't break. Right. So last thing is the video. So at that point in the flight, I knew everything had worked apart from I had no idea about the video camera. When I look at home, saw that. And now you know why I use carbon fibre. You can't see it. That's the balsa wood shadow.
Can't get around that.
Can't get around that. And you can just, if it eventually goes below the horizon, you'll see the balsa wood. There you go. But otherwise. Cool. That's it. 4 minutes ahead. Any questions?
What altitude did you get?
I think it's about 37 kilometres. So, which was almost a record back in the day, but it's nothing now. So, I mean, anything above 20 kilometres gets that sort of picture. And the higher you go, the more footage you'll get of that sort of thing. But, you know, if you took two photos, one at 30 and one at 40, and said which one's which, wouldn't know. But yeah, it's about 37.5 kilometres. And it was pretty much on target, so it was pretty close to the kind of modified prediction I had at the time. Any others?
Do you have anything else on your things to do?
Oh, yes. I wondered if anyone said we're going to do an Apollo 13 one that explodes, and I'm thinking of it. I'll have to buy another kit and not glue it together. I was thinking of like a CO2 cartridge. And, yeah, I did think before, because I had a bit of time before this about, because I glued all this, made it, painted it, glued it quite a while before the flight. And I did think, if I hadn't glued it together, I could have them docking in. That's too much. You have to set a limit and get something that's achievable, so I did that. But as regards putting things in front of cameras, I'm done now. I say that, but I don't think I'm going to beat that one.
Did you?
You don't believe me either.
I think you're never going to beat Red Bull, Ted Bull.
Ted Bull, yeah, that was quite fun. Well, you can go higher than that. So yeah, I deliberately didn't beat his record by much. Because it was set to just a few metres above his record.
Should have gone higher. Should have gone higher.
The balloon didn't go, so I think it's 41, 42 kilometres, so another 2 kilometres or so. So yeah.
Is that paint, that gold?
No, it's not gold either. No, it's foil. They give it as part of the kit. So it's just aluminium foil that you scrunch around.
Right.
Yeah.
It's gold coloured.
This gold-coloured aluminium foil. Yeah.
It looks good.
It does. Yeah. I mean, it's a superb little kit. It was fairly tricky to make, but you know, but they didn't supply all the colours. There were one or two, and also the pattern of the white I had to kind of guess from photographs because they didn't really show where to put it. But it was annoying because I painted those as solid rings till I noticed that the manual didn't say that, so I had to go over with the silver stuff afterwards. But, anyway.
So Dave, did you use Laura?
Yeah, all of it was Laura. Yeah, did I buy? I can't remember. I may not have even bothered RTTY at all. I don't bother tracking RTTY myself. I put RTTY on just to help because you get more people listening, and it's a more interactive thing, so it's more fun for the people listening. But for me in the car, I don't even turn the radio on for RTTY.
Because you needed the gateways or anything.
For this stuff, I needed the gateways. So yeah. So I don't think I flew RTTY at all this time. But no. Law is much better in the car because the amount of kit you need and the amount of maintenance it needs is much better. I mean, like I say, I've got a phone. Once it's locked into the signal, it just works. And you could, I mean, I've got a load. I mean, I could have done a half-hour talk just on the kit in the car, but you can there's just a phone and a low receiver is all you need to go and track one of these from launch to chasing and on foot a whole lot.
What was your backup tracker?
Sorry? It's a little Upu Sonics guy, and Anthony. He made some trackers a while back, and Steve was going to do a flight where we're going to launch a load of balloons at the same time. So I've got about 10 of these, and I just put it into that little leg, and I just attach it to basically every flight because it's 50. Yeah, it might be less than 35 grams, I think it is. So you just stick it in line, and it's an extra backup because stuff goes wrong, you know. And if the tracker's working, the aerial can get ripped off. I've had that. All sorts of things go wrong. Another backup tracker is very unlikely to do.
Backup tracker tomorrow as well.
Yeah.
Cheers, Dave.
Cheers. On time. I can almost sit
on time. Yeah, you can almost sit down there. Right. So apologies for the next presentation. It's a little bit rough because. Oh. Good. Something. Don't worry about that. Because I don't know. No, it needs more production. That's that. This has been sort of like put together at a few days' notice, and it was something that I put together for last year. And when I was looking at the slides, I was thinking, I don't remember what I was going to say here. So we'll push through.
Yeah.
Okay. Yep. Cool. So let me put the thing on, Dave.
Oh, sorry, you need this.
The microphone. Oh, actually, I'm going to probably do that. this is something that we've been doing one form or another for a long time. If I remember back, I might be remembering wrong, but I think I originally put some landing spot prediction in one of my pick-based trackers before we had the tracker. So if we go back 10 years, some of the software that we use today wasn't in existence. And although I think we had the predictor at the time, we didn't have the tracker. That's as I remember it. And so it was sort of an impetus for me to come up with something that would predict the landing spot. And so I ended up doing that on the pick by looking at the ascent profile and using that data to predict a landing spot. There's a few tricks you can do in maths to make it easy, which you needed to do on a pick because a pick's got, the type of pick I was using has got no memory or anything. So, right, so why do you want to do landing spot prediction? Well, obviously you want to go and get your payload back, but more than that, if you get there early enough, you can take some nice shots like this. But also, the key thing is safety. So if your payload lands somewhere where it shouldn't, like a road or power line, I've had both of those, you want to get there quickly. In fact, you want to get there when it lands so that you can, guide people away from trying to pull down your payload off of a 110,000 volt power line. So that's really why I want a good landing spot prediction. So here are a couple of videos that this is stuff landing. Don't get to see it actually.
BBC one that touched the line?
No, this didn't touch the line. Oh, the BBC, one of the BBC ones, yeah, touched, landed on power line. Yeah, just when you don't want something to land on the power line, it will. And you can see there's power lines everywhere here. So that's one landing just in front of the power line.
I love the way the parachutes slow down when the payload hits.
Yeah, because they're suddenly taking all the weight away. So these are a different flight, a little bit further away, so a bit more of a dot. So this is another, again you'll see that this didn't land that far from a road. But it's really good to see where, in terms of like getting there ahead of it and seeing where it's going to land. So this is an interesting shot. This is taken off some of the footage from another flight, and it's been stabilised on the parachute. So it's a handheld shot that's stabilised on the parachute. Yeah. And you can see the motion of the payload underneath the parachute, or you can see the parachute coning. So it's one of the reasons I like to do it is you can see what's going on in the descent. You see the stuff wobbling there, like sort of oscillation motion. So again, if you're getting there early enough, ahead of it actually landing, you can you can capture that sort of data. This is a final one. This was actually visible for ages before. This was recorded on my phone, so it was like handheld stuff. It's been a bit enhanced since. Why it's not done this way? Yeah, I hope there's no swearing on it. As you see in a minute, it didn't land that far from a car, but fortunately it landed in the trees.
You don't hear that.
So that's, in essence, really, that's why we want to do landing spot prediction, so we get there early. If there's any issues, you can help mitigate them. How do we get to the next slide? Oh, okay, yeah, that's what it is. So, do I need to get back into? Is this? I've done something, Yeah, 6, 11. Well, actually, I prefer rather So with tracking, or rather landing spot prediction, we do in a couple of different ways. There's the HabHub tracker, which does a prediction on descent using the data it's received or receiving from the payload. It adapts the, or I hope it does, adapts the descent rate. But it actually, as we both noticed, it always predicts long, and it does that pretty consistently. So it's not good at predicting the landing spot. So, but it does work and gets you in the general area. And all of those flights were done using that, to get there first. But what it's doing is it's taking the data from the descent and using wind models it's got from GFS to calculate a landing spot. As I say, it adapts the descent rate, but it's got its limitations. So onboard flight prediction uses the ascent data to build up a profile of the winds as it's going up, and it uses in descent. It uses that same data to predict, where the payload will land. Again, it can adapt its descent, rate calculation using like real-time data from the position. It's obviously finer resolution, but because it's getting updates every second, but obviously you get a lot of GPS noise in that. So it's probably not a good idea to, you need to adjust your sort of sampling period so that the noise becomes less relevant to the landing spot prediction. Otherwise, you get a lot of changes. So yeah, and we transmit the landing spot position, calculate land spot position in the downlink, and that means that you can actually just receive it offline in the car. So if you're driving around, you've got a prediction from your payload. If you're in contact with your payload and can hear it, you're also getting a prediction about the landing spot, which if you're driving around with the HabHub tracker and you lose internet connectivity, you've got no idea what the current prediction is. So it's good from that point of view. And there is at the moment a way of putting at least one X on the map at a time. I'll come on to that in a later presentation, but yeah, you can put an X on the map, which is like a landing spot prediction as it's coming down. So the next slides are really just sort of explaining the process of calculating the landing spot. So as you're going up, you literally capture the latitude, longitude, and altitude, and then you create a wind model as you go up with vectors of either a vector and like a speed for each of the levels, or you can. The way I do it is recorded as a latitude vector and a longitude, and as you go up, you just hold that data, and you can use exactly the same data as you're coming down to calculate the landing spot. So yeah, as you're going up, you're calculating these wind vectors all the way up, and then on the way down, you're using those exact same wind vectors to calculate where the predicted drift is, and sort of like summing up each of those vectors to calculate a landing spot. Now, with the original stuff I did on the PIC, you couldn't do that because, in essence, the PIC wasn't capable of storing all of these wind vectors all the way up. So I used to just calculate on the ascent. I think I calculated the predicted landing spot, and then finally at burst you would hold that, and then all you would do is adjust the rate as you're coming down, and that would just change the landing spot. So it's actually true that once you've got all these wind vectors in the descent, the model is such that if your parachute is half as ineffective as a different one, and it's all landing at twice the speed, the predicted landing spot will be along a line that just gets longer or shorter, depending on the actual descent rate. It's always in the same direction. That's not changed because it's always following was effectively a multiplication of the descent rate. So what's the accuracy of this sort of calculation? You've got to have a good descent rate model. You need something that gives you a model of the atmosphere and it's on how much drag you will get from your parachute and payload. And if with a good model, you can get some quite good results. But one of the things I have noticed, and we'll come on to it in a slide in a second, is that it's not always that repeatable. So even if you've got a good model, the atmosphere actually is not that consistent. I mentioned the GPS noise. You're not really sure of your position exactly, so you've got some uncertainty there. And it doesn't take into account anything like a vertical wind, which I get the impression certainly happens. Certainly close to the ground, when you get thermals, you've got like a vertical component to the wind, and it's not really taking that into account. You'll see some of the graphs in a minute that indicate that. Duration and distance of the flight obviously affect this. The longer you're in the air, the more out of date that the ascent model is with the descent model. And distance, again, if you're further away, a lot further away from the takeoff point to the landing point, then the wind can be quite different from what happened at ascent. But it's pretty good for general, what we call, up-down flights. So this is about calculating that drift, and really it's a very basic equation that we use here, which is the old drag equation. If you're into model rocketry, you'll know what it's all about. It's basically drag from the parachute. One of the things that you'll notice is actually a number of almost fixed terms here. The weight of the payload doesn't really vary. Maybe gravity is fractionally different, but it's very, 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 very small. The area of the parachute's the same. The coefficient of drag for the parachute doesn't change. There's a thing called Reynolds number which can affect that, but actually I'm told anyway that by people who know parachutes that they don't really change the Reynolds number for the unlike the balloon actually in ascent, which seems to change the Reynolds number. And the only thing that really changes is the density of the air, that rho, that factor. So using this, these basic formula, you can actually calculate the time it takes to descend through a particular level of air, and therefore, if you know the wind speed and direction, you can calculate how much it's going to be drifting by. So you just really sum all of those up on the way down. So air density models, there's several you could use. These are the ones that I've been used in the past. This is an incredibly simple model. It's not as good as this model. This is a NASA model that was produced in about 1970, but it's public domain. There's some much better ones now available, but they're a lot more complicated to calculate. So it just really comes up with a density for the air at any altitude, certainly within balloon heights. But all of that relies on the fact that the atmosphere looks like that model. So here are some flights that I've done in the past that use the same balloon, the same fill, the same parachute, the same and everything. And as you will notice, they are actually these are the ascent profiles. They're quite different. They're obviously in different days and different times of the year, but you can see that sometimes there's some elements of the shape of the profile is the same. Maybe those are a bit similar. But this one, comparable with that one, completely different.
What is the x-axis?
Sorry, this is ascent rate here. So they're all centred on the same rate, which is about 6.5 meters a second, because they're all the same. But that's altitude. So the higher you go, you get this sort of change in the shape of the ascent rate. There's this thing about balloons as they ascend, changing the Reynolds number changes. What's effectively Reynolds numbers is about the way that the air flows around an object, and then behind it creates a wake or turbulence, and like pulls back on the item sending. So it's shape dependent, but it's also density dependent in some cases. And for a balloon, or spherical object, it is. So that gives you that's just really to show you that no matter how good you might come up with a mathematical model, and unless it happens to magically know what you're going to get, you're never going to get a perfect calculation of the atmospheric density. This is a graph of effectively a parachute effectiveness. It should be a line straight up from 1 there, which is like consider it to be like a coefficient of drag value. This is calculated from the but you can see actually that effectively the model, this slope here says that the model I've got is wrong. Basically, if the model was correct, that would be a straight line vertically there. So even the NASA model that we're using is got some difference from reality. So there's a couple of slides here. These are landing spot predictions through descent for 2 different flights, and the reason that there are like 3 graphs on it, 3 lines on here, is that these are 3 different methods of smoothing the descent rate data. So I was sort of experimenting with different algorithms for trying to take out this noise that you get in the GPS noise. So the landing spot is actually here, down here, and the start of descent is there. So that's balloon burst. And actually this is only, 2 and a bit kilometres out. So even at burst, it's 2.5 kilometres out from the landing spot prediction, the actual landing spot. And then as it comes down, you can see it actually spends quite a bit of time there. I think once you're down to like below 10,000 feet, 3,000 metres, you're down there somewhere. So you're getting less than 500 metres from the final spot. So this isn't actually the path; it's the predicted landing spot changes. And the same is true of this next graph or diagram, where I was again using some different types of algorithm for smoothing. So you can see actually they result in quite different values to start with. But these 3, look quite promising. The actual landing spot is there. So again, this is about it's 200 metres for that. So it's probably less than 1 kilometre at burst, and then getting better and better as it comes down. So Dave, your bit.
Oh, okay, yeah.
Do you want to swap over?
So my section is just about how Pie in the Sky implements it and how to configure that for your flights. So obviously the Pi's got lots of memory, unlike the tiny little PIC that Steve used. So it can do all the store all the delta that's on the way up. And what it does is it chops the atmosphere between launch and 40 kilometres, I think. Actually, I set it higher because some balloons go a bit higher than that. Into 100-metre layers, and then for each layer it stores, I can't remember exactly what it stores, but it's basically the wind vector for that layer. So it knows when it enters that layer, knows when it exits, and knows the difference in longitude and latitude, and also how long it took down to that section. So at the end it will say the wind's 5 metres per second that way, for example. Then I used that NASA atmospheric model, so it's basically code I stole from Steve. And the default parachute performance and payload rate figures, so those go in the PySky.txt configuration file. So at burst, in fact all the way up to burst, it's predicting based on the data it's learned so far, plus that standard parachute descent curve based on a 5 metre per second landing speed. But even if you get that wrong, as soon as it starts descending, it will adjust itself because it will compare that theory with practice and say, no, it's actually going to be a 6 metres per second landing speed, therefore the curve is this instead of this. And then it will apply that to all this data here. So that's what I said. And so essentially it's saying, well, I'm here now, I've got this vector, this vector, this vector, add them all up and say that's where you're going to land. Steve mentioned about noise, which is GPS noise, and I think there's some up and down wind noise as well that goes on. So you'll find that the prediction, if it says it's going to land there, it will do this on the way down. It won't do this thing, it will just be the distance. Default 5 meters per second, yeah. And the adjusted parachute performance it emits, if you ask it nicely, it will emit that in the telemetry, so you can then, and that's logged on the SD card as well, so you can see how well the prediction went afterwards. So that last thing there about the telemetry, you can, well, okay, first off, in the PySky file you need to say, do me landing prediction. And I think if you're flying high in the sky, you should do it. There's no reason not to. These values here, I think actually those might not be the real defaults, but anyway, the default's in the file as it comes for 5 meters per second landing speed. I should have called that landing altitude, but the target altitude, as in where you expect it to go. Now, for Steve, you could just put it 50 and it'd be right every time, wouldn't it?
That's right.
For me, because I'm near Wales and hills and things, so. But to be honest, the odd 500 metre altitude difference isn't going to make a lot of difference to the landing anyway. And then the last thing is this, which Steve touched on, and this is saying it's going to emit the telemetry as a payload called XX, which is a magic keyword. If you look at the spacenear.us code, it says if payload ID equals XX, don't draw a balloon, draw a big red X on that. Unfortunately, if 2 people do this at the same time, it's going to have 2 X's doing this. And it's we've done requests on GitHub, and no one's done it, so maybe I'll just have to do it myself. But anyway, it'd be nice if we could say XS1, 2, 3, 4, and nothing on that for different flights. But at the moment, you're limited to 1. So at the moment, I suggest you don't do that. If you don't do it, if you basically comment that line out, you get all of the this data here is added to your regular telemetry strings. It's just added onto the end. So as well as your regular latitude, longitude, altitude, you'll get predicted latitude and longitude embedded in the telemetry. And including time to landing, which is I find that quite useful one, just to know how long you've got till it lands and how much you need to break the speed of it flying together. So, and if you do the XX, you don't get that. You just get a payload message with latitude, longitude, altitude is 0, just to keep the map happy, and that's it. Checksum, nothing else. So having, I mentioned earlier this Android app. You can see my childhood influences. It shows this is a particular payload. That's the current position, altitude, it's on the way up obviously, and that's the landing position. Not a useful thing yet, because it's on the way up. But so what I could do then, and if you're chasing a balloon generally, after it's burst, you just want to go for the landing prediction. If nothing else, type into SatNav and go. But on this app it's a bit easier because all you do is go to this page for direction, it tells you where the balloon is. If you click that button, use prediction for navigation, and then click that, it'll load up Google Maps or whatever your default mapping, driving instruction application is, and it will take you there. So you just follow the instructions. So if you're a sad person like me, chasing balloons on your own, maybe just do that and just follow the instructions with text as you go along. Text instructions, turn left, turn right, do that. That's quite nice. It's got other things there. So these 2 buttons, this to be an advert for the app, but that button there is the same thing, but it will load up an off-road application instead. So I use a thing called Backcountry Navigator Pro, but there's some others, and that will give you the off-road bit. So if you're on foot trying to find public footpaths across fields and that kind of thing, I use that. And the last one is just show route, which I think is the next slide. So I've done show routes for flight, test flight, not the real one, and Google Map here is just showing me the route. So So at the moment you do need to be online to get this bit going, but if you've got offline mapping app, well, you don't need to be online at all for this application. You can find a route anyway. And that's that bit. Steve, anything else?
No, I don't know. Has anybody got any questions?
So if we don't put the predicted ID in .x,
yeah, if you don't do
then
that,
we have to add it to our flight, not our flight document.
the payload document. Yes. Yeah, so if you don't do the XX thing, then added on to the end of your regular telemetry, temperature, pressures, everything else, will be that lot there. So you have to go to your payload document and fill it in. I should mention that if you can get the best of both worlds actually. So if you want the XX on the map, but you want, see my application does the direction based on the embedded telemetry. Yeah. If you want the best of both worlds, so you want the X on the map as well, you can do this one here, so it's embedded, and I've got a little Python script that grabs the position from HADHARD and uploads an XX remotely, so you just run it on a Pi at home or something.
Oh, we could leave.
So you can do that.
If it's bit have RTTY with XX and LoRa with getting telemetry.
No, what I'm saying is, no, it's global. If you do that,
of course, yeah.
if you do that, all the transmissions, LoRa and RTTY will do it. Yeah.
Well,
So, okay, let's just change the code. But no, all you need is a few lines of Python, and it just reads that stuff. So the rule is in your payload document, you have to call it either predicted longitude or pred underscore longitude, I think it is, and it picks those two values out, and then creates an XX sentence and uploads it to HADHARD, and then it appears on the map as well.
And that would presumably make another
XX if there was one.
So,
Yes.
but you're running this Python script at home.
Yeah, so that's one at home. Yeah. But my focus normally is on what's in the car, so I try to be offline, so I don't really care about what's in the map too much. So I tend to use this stuff. And that in the car was just great. That's what you need. And before this, I'd get that from the telemetry, and you kind of write it on a bit of paper and then type it into your sat-nav, and there's always an error somewhere. And now it's just click up the button and it does it.
To establish your speed as you're going up and coming down, are you holding the GPS really rapidly?
No, it's 1 hertz. It's 1 second, same as
What's a second?
Yeah, it's fine. Nothing, because my vertical layers, my slots are 100 meters, so that's 20 seconds worth. So you 1 hertz, that's fine enough to, yeah. And the next 100 meters isn't going to be that much different.
Do you actually use 100 meters, or do you use what it happens to be at this point in time?
No,
near
I do 100
okay, you actually
slots.
calculate like the boundary.
Yeah.
Okay.
I was just thinking in terms of errors.
Yeah.
You know, if you're when you're going up, particularly when you're coming down, I guess if you have an error between your 100 meters, if you're at 103 or 97, given the levels of accuracy you're running at, perhaps that is generating some kind of.
If I remember rightly, I might be pretending I coded it more cleverly than I did. It interpolates, but it says so it says 95 and then 105. I think so. I don't think the error was huge.
I mean, I've done a similar implementation on the Pi, and the way I do it is, it's the next reading I get beyond a preset value. So it's not fixed boundaries. It's sort of they're similar in size, but it doesn't get any, you don't have to do the interpolation. There's so many ways you could do this.
Yeah. And the biggest error is you as well. The biggest error is modelling the parachute descent with that GPS noise and with thermals messing you up.
Yeah.
So, on those charts earlier, you saw quite a lot of noise at the top, and then when it gets down to the troposphere, it's like this. And the result of that on your prediction is it says that way 500, no, 200, no, 600, and you get a straight line, but with a lot of error on it.
The worst area I found is when it gets close to the ground, because you do get thermals there, and then you either get them or you don't. You know, some depending, I think, whether you're crossing trees or something, and if you cross a river, that's also completely different.
It's swinging in the majority of the masses at the bottom. That will be the influence of the speed at which it's coming.
Yeah, that gives you a.
You're right, because on the way down you get a lot of this going on.
I still think it's amazing when you see these things for 20 miles, you drive 100 miles away and the thing drops out of the sky.
Well, you said it.
It's reasonably doable. Yeah. Well, I've seen people do it on their first flight actually. So, but I think they've been lucky. But you know,
I mean, to see it, you need not trees on the way and stuff. And you need some luck. I mean, that follow one I did earlier, I knew there was no way I was going to see it land because it was just so far from the road. You know, it was covered with trees everywhere. But out of my other last 5 or 6, I've either seen them all land or I could have if I'd tried.
East Anglia is good. East Anglia is good where I do it because it's flat. You know, you can see for a long distance normally.
As regards thermals, basically, if you've got nice, well-formed, flat-bottom clouds, you're probably likely looking at 3 or 4 up as they pass. So if it breaks and comes underneath, it will suddenly change under some.
Actually, I should go back to one.
So forget the camera to take some photographs on the way out. No, that's a cloud. Oh, yes.
Well, it's those sort of big, fluffy marshmallow, but with a really well-defined flat bottom. Completely.
That's what all these are here. It's just as it's got close to the ground, the descent rate, suddenly improved by a factor of 2.
On the plus side, but when it's down there, it's only got a couple of meters vertical. Anyway, so
but if you
someone might be talking 5,000 or 6,000 feet cloud base.
I was just saying about the noise down here.
All right, sorry.
But
they can certainly make a difference between seeing it and it being
over there.
It can certainly be. If it gives you 500 meters over, that could be. You should be the other side of the field.
I don't know what we do about that, though. I don't know how to improve that.
Well, then tell me where they are, because I can get
Yeah. We'll look for the clouds, I suppose. Have a camera looking out.
No, you can't. There's nothing you can do about it, but you will get a big change.
Yeah, sorry. Robert?
Just a question there about your pie in the sky. You're coming back with LoRa?
All of this would work with LoRa or RTTY. It's both. Oh, okay. What I've said here applies to LoRa or RTTY or both, whichever you have.
And so you're going into the Things Network, and then with your HAB Explorer, you're going into that?
Right, okay, so that is working offline for a start. So, and if you look down here, these are the different sources for data. So this is USB, so I have a receiver plugged in. I've got Bluetooth version, which is that one, so I can run 2 different frequencies if I want, and then Habitat. So basically, once it's received something locally, then it adds it to a little list of ones to ask Habitat about. So if you're online but you've lost local data, it'll fill in from all the other receivers.
So you've got to be able, when you're online, you're going into the Things Network?
Well, it's our HAPOD network, it's our Blue network. Yeah, but basically, if you're chasing a balloon, you should be able to get a signal yourself. Especially when it's landing, because it's low. Usually, the only time you don't is when you're so good at chasing it, it's right above you and the signal does propagate vertically. But the rest of the time you should. And when it comes to low, you'll get heavy packet. So
to get the signal for the receiver?
It's a little box. Actually, Anson's making them commercially. You can buy them. But it's an AVR chip. It's basically an Arduino on a board, AVR chip with a USB connector. And then you just run a little cable into your phone. And if your phone's less than about 3 years old,
and the receiver itself is
there's a LoRa receiver on the AVR board. So I've got one in the car, but I just hold that with a little rubber duck aerial and run around with that.
They clarifies.
Sorry?
They clarifies.
Okay.
Following on from that, just looking at your text and explanations of HAPSCORE and HAPPAD on your website, you say you support other modes. How do you get RTTY into that?
Right, so this one's a bit limited more because of I've run out of space for the buttons for the settings, but that's the phone version, and I've got another one which is for a tablet, which has got a lot more. RTTY, if it's DLFL Digi, I've got a program you can run on that PC, which broadcasts the telemetry as a UDP packet, and then it gets picked up by the tablet. There's a guy who wrote another decoder, which is more kind of hands-off one for a Pi called Habdex. So you have a Pi and an SDR, and again, there's a little script which takes the telemetry from that and broadcasts it to your UDP packet. So as long as your Pi is on the same network, so you use your phone as a Wi-Fi access point, and then the tablet will pick up that and it will go on the map. And the same goes for DarkSide's SOND receiver. So the Auto-RX, that has a UDP packet setting, and you just set that to the same ports that you make the tablet listen to, and it will appear on there as well.
But the least number of sets is plugged lower via OTG into either phone.
Yeah. Yeah. Yes, absolutely. Yeah. But if you're flying, chasing radio SON, then you want DarkSide's thing on the same network as the tablet, and then that work. Bohemians can do that and chase them. For me, the closest gets launched in Cornwall, so there's not many times it'll come up to where I am, but Bohemians can chase it. But the car set's already. On the tablet one, there are more sources set up than this one. This is more those two there, USB, PC, Habitat.
Right, thanks, Dave. Is it fits quick? Yeah.
I was just wondering, this method of using the ascent to predict the descent, can you use that at all on the ground, or does that really have to use the really high frequency data on board?
I've done it using the data that's been recorded from on air. So those graphs that you saw earlier were taken from the landing spot predictions were just basically taking the data off of HabHub, and so it's every 15-second data.
Sorry.
Yeah.
I mean, basically, what you're doing is you're adding up all your deltas, aren't you?
Yeah.
You go up and then back down. So then there's a change of position as you go up. You can sort of do that as an addition up to that altitude anyway, and then add those on at the end, but in reverse.
Yeah, but the ascent is basically 5 meters per second constant, supposed to be, but not quite. But descent is very quick at the beginning, so you can't just say, if I went from here to here on ascent, I'm going to do the same thing on descent. Yeah?
No, but is it just some sort of stretch factor? Can you?
It is. That's what I was saying earlier. Yeah, that's how the original PIC one worked. As it went up, it actually was calculating the landing spot as it was going up, and then when it burst, it said, "Okay, I know where the landing spot is," and all it then did was scaled the landing spot along that vector as it got the descent rate, because that's all it could do. It didn't have the memory to store all these wind vectors. But as you come down in descent, you can update where you actually are in comparison with what is left to go to.
And there are some flights where the parachute basically changes on the way down.
Yes.
So
that's true.
It gets tied up with a cord. Or I had the most extreme one I saw. Was a tiny little payload and reasonable size to shoot, but the balloon made a huge parachute. I mean, it was at 30 kilometres doing 2 meters per second. It's going to take all day, and it got down to I think 6,000 meters, and then obviously it was basically we made it a minute later, and then it broke, and then it went splat. So my one would cope with that, but the simpler one, the strength wouldn't.
Cool. Right, well, lunch has turned up, so I don't want to hold anybody in. You've got about an hour, just a little less than an hour now, so go feed. Right, Nick's going to talk us about Backtrack and conformal coating. Take it away, Nick.
Thank you very much. Right, so 1 year on since I spoke about the new perspective. For those last year, this may remind you of who I am. I'm the guy that lost the Bakewell pudding in space. And that actually relates to what I'm going to talk about today. I'm not entirely sure how we arrived at the title for my talk, You will find it slightly unusual in so much as I realise I have to keep you guys from having a carb-induced snooze straight after the lunch fest. So I lost the Raspberry Pi in space, which was interesting, and I got a lot of radio coverage, and Stephen Fry tweeted about it, and when we found the Raspberry, the Bakewell pudding, Tim Peake tweeted about it, and generally speaking, my name is sort of mud if you like. Do a search for high altitude ballooning, because everyone says, aren't you the guy that loses stuff? And the short answer is yes, because I then did a launch in August, got a great height, my first hydrogen flight, didn't blow myself up. We did blow the tyre on one of the cars driving down the motorway, but that crapped out as well. And that's a technical term, crapping out. It just stopped sending pictures. But we got a good retrieve. Incidentally, the rubber wrapped halfway around the parachute, hit the ground at 18 meters a second. We thought we were going to go and find wreckage, but it actually turned it all back on, which was rather handy. Then in November, being a glutton for punishment, I tried again. And if anyone wants a pie in the sky, somewhere in South Lincolnshire, there is a payload with my name on, God alone knows where. So come the start of this season, I thought, right, I really need to sort this out. So I made myself a tracker, which apparently puts me into a proper high altitude balloonist category. It's very clear that you aren't a proper one until you've made one. I had to actually use components rather than handcrafting them from bits of iron ore, but we'll come to that. But whilst I was doing that, I'd had a continuous conversation with Dave, who obviously wanted to know what it was I was doing to his kit that I managed to lose it quite so spectacularly. And after some discussion, he decided that conformance coating was the way forward. So, sorry? Yeah, that's right. So, I'm in this situation where I've lost a kit. I've had several flights, I've got the kit back, but it's not operated as expected, and all the while other people are using it and not experiencing the same results. And for whatever reason, we became slightly focused on hardware. So we started sort of snuffling around, checking things. The November was a complete new setup, so there was no similarity. It wasn't any of the same hardware at all. And obviously, because actually I'm a software engineer, hands up those who've got a license, a radio license of some sort. So that's what, 2/3 of the room? Yeah, well, I'm definitely got my hands down, only because I just didn't get around to it. It was something I was doing when I was younger, but mostly I write software that runs on little controllers and also on the desktop. So obviously, it's got to be a hardware problem. And somewhere along the way, Dave started licking his finger and pressing it onto various parts of the pie in the sky, and decided that the current revision inductor, I think that's what you told me, if you made it soggy with your finger, it caused the power supply to droop a bit. So he got some conformance, and he got a brush, and he stuck it in his eye. So that put me off for about 3 months. And once I'd got my conformance coating, because I don't really need it for the work that I do, and I'd found a sufficiently well ventilated space, as in just outside, because the stuff makes like glue sniffing like an entry level product. It really is vicious. And Dave said that he was off for a couple of days with holding his eye. Well, I'll dig out the IRC logs later. Anyway, so that's actually a tattooed one. That's not his real one. Anyway, so I coat mine in conformance coating between rushing around holding oxygen cylinder to my face, because it does actually make you completely high as a kite. I've got my backtrack, and I think before I start getting students to throw my kit up into the air, I am going to do a test flight, which was really good actually, because it was quite peaceful at the launch site for a change. I was just swearing at myself. So I launch, and I land somewhere up there, because I also have a magic tree finder. I've found a number of trees. That's actually where it was, sort of dangling down, and there's a line up there, and somewhere over here is 2 little boxes, one of which is got the backtrack in it, which was there to act as a backup, hence its name. The backtrack was configured with a Arduino Pro Mini, a relatively mid to low brand GSM GPS module, and a LoRa chip, and between, so I could get bog standard LoRa telemetry. There's a few bits on the string that might imply it's running at 240 volts, 13 amps, but I'll fix that another day. But the main thing was it also had SMS. So this thing's up a tree, and it sends me SMSs every 10 minutes for 36 hours, which got like that because unfortunately it was sending it to my phone that I use. We live in a rural area, so I respond for the ambulances. It's a loud phone. Anyway, so back to the drawing board. Now, after 10 days of recovery time, we used the balloon technology that my wife developed, which is to go and get a big party balloon, run it up on a line, hook it around, and then pull down the payload. And that works really well. That's the second time we've done that. But I now had the kit back. And it was, obviously it wasn't a conformance issue, it was something else. So it went on test for several days, and a couple more days. And then Dave made some suggestions, and we tested it a bit more, and we ended up in that sort of quasi-land of whether it's actually true or possibly false, depending on how you read it. And then I actually employed the scientific method. So I started documenting the range of different tests. But the good news was, for the first time ever, Dave could get it to do it as well. Hurrah! The expert, as opposed to me hacking around, could actually get it to happen in the lab. And after we tabulated a few things, that's just some random tabulation, it turned out that in the excitement of launching, I had ended up at May last year with a particular version of Raspbian and a version 2 camera. And this out-of-date kernel, groans, this out-of-date kernel, right, okay. I knew I'd have to keep you awake after lunch. Right, so this out-of-date kernel just happened to have a particular thing going on in the GPU component that we don't have access to, the video core, on the Raspberry Pi, that basically meant if I dumped a full-size version 2 image into it, at some point the Raspberry Pi flatlined, and it took out a number of processes that caused everything that was we needed it to do to stop. And if I had even thought that it was software for a second and I had updated the software, not PITS, just the Raspbian, none of this would have happened. And so this is a bit of a cautionary tale. But anyway, the great news was this was success. And I have subsequently flown my PITS kit without any issues for the PITS. I have found that the students have found other failure modes for me to contend with, involving weighing things, but I'll keep that for another day. So that just gives you a little sort of background as to my journey since last year. But the main thing is I now have this Franken circuit, which is version 1, that is my backtrack, and it is specifically designed just to be a backup tracker. I don't want it to do anything else. I tried to get it to do something else, but it didn't work, so cut that. box standard Pro Mini, unadulterated in any way, shape or form, running at 3.3 volts. So I've got an Arduino Nano or Uno for all intents and purposes in a low voltage small form factor. Probably a Chinese one because I bought some Chinese RFM 98. That W? No, it's not. It's just an RFM 98. LoRa chips, which I lovingly soldered some legs onto because the holes don't match. This was actually the second SMS module, GSM module. You can see there's a slight mod there. It shouldn't be modified, it just had an accident. The first version had patch wires all around the power circuitry after an even bigger accident. But these are about £9 if you buy them from China. So the accidents aren't like you've toasted a whole real thing. It was irritating, but it's sort of a fairly simple thing. We've got to convert the levels, and I just found the power was a bit unstable when I sent SMSs, so I put a huge capacitor on the side. I think that's 1 farad, just because it was lying around. I was doing some solar work as well. I did try and strap a pressure sensor on, the idea being that I could shut down the GSM module and wait for the get down to a particular altitude and then turn it back on again. But that's just saving some batteries, and I'm always putting in AA's anyway, so it was nice to have. But as soon as I included that library, I pretty much trashed the heap. It just died very quickly, or never even got going, partly due to my programming methodology. So this was the version 1 backtrack, and as I say, I then awarded myself, as it had worked, the badge of honour that is I have built my own tracker. Because it did work, it wasn't insulated well enough. On the way up it froze, and it rebooted on the way down, but it sat in the tree with one of them flashing lights, and you could tell the local raptors weren't happy with that from the noises that they were making near the thing. So, just to give you an insight into Backtrack version 2, this is the PCB that I have for my tiny thing, which is a LoRaWAN, so it's a Pro Mini, and it piggybacks onto a board that then provides mounting for the LoRa chip. So I have those available. So the form factor now for my Backtrack is just this size, and you can see that the brake, and it sort of makes it sort of about that big in total. And if I flew that with some AA batteries and a boost converter, I'm not quite headed towards the backup tracker that Dave gets from Anthony, but I've got something. Partly while I was doing this, because I work with schools mostly, I've used all of the big S string stuff, which is why I couldn't get the BMP pressure sensor to fit in. The reason for that is that this isn't going to be published as a finished solution, because if I do that, the students will just find it and copy it off the internet. So what I'm going to do is document this, so that if anyone has a burning need for a backup tracker and just emails me and says, can you just send me the stuff, I'll do that. But if I set a challenge to an A-level student cohort of linking this stuff together and programming it, I personally would find it easier to cope with their new coding skills if they were using the big S strings, which we all know are naughty, but will enable them to make reasonable progress with the thing. I have a redacted copy of Dave's LoRa library, so it only does transmit. It's removed everything, but everything else was coded from the ground up. And that's it. That's my last year of becoming. What do I go from noob to? What's the next level? Apprentice. Okay, I'll go with that. No. I mean, I've only actually flown twice now this season, and definitely got. What was it? 3 times. 3 times this season, and definitely got the damn things back without too much kerfuffle. But I've got a very clear picture of progression. There is some element of debate about whether we can expect people early on to build a tracker in their own right. If they're not studying some electronics and some coding, that is quite a task. I soldered it together in an afternoon, but I'm a software developer. It took some while to get the GSM and the GPS all piping stuff through to the LoRa.
Just with GSM, I'm curious, because we're fairly new to it.
Right.
But has anyone else played around with GSM modules? You said you put the great big, was it a barrier and capacitor on it?
Well, it was just one. I now use a 470 microfarad, but yeah.
But we had sort of similar power issues, but we realised that a lot of it is because it has these huge sort of pulse currents that it sometimes drop. Have you found that it interferes with anything else? Because we had a lot of interference. We put a cosmic ray detector up, and we found that there was enough power transmitted through the antenna that we were reading those as cosmic rays.
I haven't flown a cosmic ray detector next to it, and it's in a separate small box on the line. GSM is I included GSM because I just wanted some other percentage chance, and each time I've flown it, I've got either a lot of messages for 36 hours because it was at the top of a tree, or I've got a message about 200 meters above the ground because it's taken that long for it to get a local signal and then get the message out, and then it hits the ground. So the 2 other times it gave me the general location, so if the rest of it had gone south, I would have still had a rough idea where it was. In the fullness of time, as my confidence builds, I may just not bother with a GSM module at all, because it is clear that it can't acquire a thing fast enough.
A pain, because I was just wondering, because you all done a lot more to the stuff, whether anyone else has found sort of interference issues with, I think we were playing with a 7800 module when we were playing around.
Well, you can test it on the ground. No. So as I say, it was 5 meters away from the main payload anyway. So because I put it 5 meters, 5 meters payload. So. Any other questions?
I saw your GSM module there. There's a GPS as well.
Yes. So it's a GSM module. It says this red bit, a SIM 808, which is relatively inexpensive. And that has both GSM, GPS, and can do GPRS if you also want to talk across the internet via it. But it does have this problem of it's got to acquire a GSM signal, preferably before it ends up face down in the dirt, because at that point the antenna then can't hear the signal. But it's relatively inexpensive. It doesn't do the fancy stuff, but it's working. As a pragmatic backup, it's working. And as I say, for me, it's a good way of showing something to some students and say, I want you to build something like this, without them having to sort of start getting chips made from scratch using cat's whiskers or pinions. Any other questions? Stuns. Oh, sorry.
You only seem to have said you painted or inducted.
Oh, I actually covered everything, literally. Oh, I had a merry afternoon. So if you think of a pie in the sky sandwich, as I call them, anything that didn't need to have fresh air, and there's some sort of bits that Susan would like, little waves where the brush. Yeah, I went to town on that bit. I may have been influenced somewhat by the fumes. They're not as good as the stuff I use for gluing acrylic though. That's really good. Anything else? Say at the break I'll leave these bits of gubbins for anyone who's interested in such things to have a poke at and critique and tell me whatever.
Cool. Thanks, Nick.
You're welcome.
Have that. Like that. It's me. I'm next. It's
insurance.
Insurance. So this is a very short little topic, really. It's the reason I'm bringing it up, although some of you probably know, is that we've found that we can get insured for high altitude balloon flights in the UK through the BMFA, and as far as I know, for like personal flights, that's about the only way you can get insured. You've always been able to get insurance for commercial flights at a fair cost, but the BMFA is now offering flight insurance for flights. I think the cover is £5 or £10 million, so it's fairly significant cover. It's a similar cover to their standard insurance that they use for model flying. And in fact, it's an extension to that. So if you're a BMFA member already, then you need to buy an extension to what you've got. And if you're not a BMFA member, obviously you've got to join first. So the total cost is about £110 a year, something like that. For, as far as I know, as many flights as you like. They ask you to fill in a little questionnaire about what you're planning to do with it. But primarily, the wording's on there, but in essence, it's for non-commercial activity. Where commercial is sort of defined by the CAA as not aerial work. And aerial work is really where you're making money. So what is allowed is, for example, I can have this to do development of systems for my business. So provided it's not, you're not making an immediate gain from the money. So anyway, have a look at what the BMFA say about it, but I'm just really bringing it to people's attention that you can now get insured for what we do, and that can only be a good thing. I think at least it gives us that option, whereas before it was pretty impossible to get insurance for anything other than commercial work. So that's their URL if you're interested, and if you look on their page, you will find there's a link to drop down about insurance and take it from there. I mean, I'm a BMFA member from doing model rocketry and helicopters and all sorts of things, but so it's just really, for me, it's just an extension. But I think it's worthwhile. Right, so that's really done.
Broadly speaking, what is the insurers want for commercial? Just to put it in context.
It does seem to vary, but about 1,000 a flight, something like that. It's not untypical. I remember one being even more than that because we were flying out of the football stadium, and they were worried about, I think, probably like infrastructure getting damaged during the launch. So it varies from time to time, but from place to place. So totally, not useful for just the odd little flight somewhere. But
there certainly sets the school's minds at rest when they worry about such things.
yes, well, I would have thought.
I am insured.
A number of organisations are insured. So I've done flights for other companies where their insurance covers them for that sort of, covers them for any activity as relating to their work. So, okay. It's not that I need to do the that's a separate server support.
Oh, there you go,
Another one by me. Again, this is a fairly brief topic, but very important. So we've got a number of platforms as UCAS. We've got Tracker, we've got Predictor, we've got Wiki, all sorts of things. And there's obviously software and hardware in order to run those services. Currently, those services are running on servers that are being paid for by Ubertronics. That's the one that you can get the Pint Sky stuff from. And so they've been paying for it for us for a long time. They've got no immediate plans to kick us off or do anything different, but it might need to change in the future. So we need to bear that in mind as an organisation. Is that this won't go on forever, and we need to be looking at a plan to move us away from that situation. So the immediate concern, though, is one on software support. There's the ongoing maintenance of the platform, applying patches, security patches, that type of thing. They need to be done. Occasionally we get things like the GFS model changes its interface, and that needs to be adapted for. Or fixing problems like we had the issue with the platform running slower, that type of thing. So those things need to be addressed, and there will be undoubtedly at some point some physical changes. But one of the areas that really does need some work done on it is platform enhancements. There's a big opportunity here for people to add to our existing platform. We've already seen a number of times today where things like the multiple landing spot predicting things really needs to be added to the tracker, or just entering a flight needs to be made easier. It's quite a complicated process. A number of people have said to me, they're completely lost at the process that they have to do to get a flight logged. Well, it might be clear to people who have been doing it a long time. It needs to be made simpler, I think. Things like LoRa needs to be integrated into the flight parameters, and also things like it would be really good to be able to enter where you think the balloon's going to burst. You've got a faster ascent rate, you think, than standard. So that type of thing would be good to add to the tracker. So there's plenty of things that need to be done to the existing software to improve it, and really basically need some volunteers to pick up that work. And I think the initial thing is really for somebody to go in there and assess what we've currently got, what level of documentation there is for it, what we need to do, and to look after it in the future. In the midterm, we need to have some people to start migrating what we've currently got to other developers. Adam and Daniel, who wrote a lot of the software in the first place, so quite happy to look after the predictor for some while. So that's one area we don't have to have like an immediate teaming for. But yeah, we need to look at funding for servers and everything else in general. So there's a suggestion to set up like a non-profit and have some accounts made to handle some money. So we'll be looking maybe for donations by commercial people like myself who fly flights and make money from that. So then maybe putting in money. And as I think was suggested by I can't remember his name, that Google Maps we've got like currently an issue with. I don't know if you've noticed, occasionally it sort of like drops out, and it's because I think that we're not being seen as like a non-profit, so they're like accounting against the key that we've got. So in general, if anybody wants to come to me with an offer of support and or funding, then I'll be glad to start pick this up in the first place and start running with it. But I'm really looking for somebody to lead the investigations of the existing software and platforms. That's my initial thoughts. I don't know if you've got any questions on that, but
can you give us an order of magnitude on the funding?
No, I haven't got a. Nobody's really looked at it in any depth. It can't be huge because otherwise Ubertronics would be noticing it. But you know, it's a big piece of work from a software point of view. I'm not so sure on the costs.
It's not going to be much less than, unlikely to be less than £50 a month, unlikely to be more than 200. But that's a wet figure based on what I see from the outside.
No, yeah, you're probably right, Nick. But need to look at it. Yeah, need somebody to have a look at it to start with. Yeah. Right. Okay. Who's on?
Question for you.
Yeah.
Where's the system actually physically located?
It's in Manchester. Okay. Most, as far as I understand it, it's all in the data centre in Manchester. In fact, surprisingly, almost everything it seems to be there. I was surprised when
Do you have any idea of the specification of the system that we're running upon?
No, not really. I think people do, but I haven't. It stands about a quarter of a rack or something.
Yeah, I think either Adam or Daniel said something about.
I don't know enough to really comment on it. Oh yeah, it's not a big platform. There's probably some fair. There's probably a fair bit of data going to and from it. You've got a GFS model going every 6 hours. Yeah, so sort of 8 gigs every 6 hours, I think, something like that. Is it 14 now? Yeah, it's probably gone up, hasn't it? As a result?
It needs an evaluation.
Yeah. Yeah. Right, so anybody who feels that they could help in that matter, then please get in contact and we'll take it away from there. Right, who's up next?
Do we know who all the commercial operators are? You and I both.
Well, no, we don't. I know a few. You know, there's you, there's me, there's Sent Into Space, there's what are the Astro something or other. Yeah. No, these guys are like based in.
Well, there's people on the world who go to schools for charge.
Okay. Well, it could be Sent Into Space.
Just before we crack on, how do people feel generally about if they did make a donation each time they did a flight? Because that's when the service is stressed the most. You know, if you were asked, oh yes, we can see you doing the flight, can you pay £10 to help cover the cost of service?
Yeah, I think it's an amazing free resource and hardware, and in my experience, people go from being off the program nothing to now making their own balls up. There was the only thing I think on the paper just some kind of scale thing, so you do it the first time it costs this.
I think.
But maybe you get an annual fee and you get as many as you want. Because,
well, maybe what we should do to begin with is just set up a donation things and see how we go on, and then if it doesn't start rolling in appropriate quantities, then we can start squeezing people for money.
I think as long as the commercial operators pay an amount commensurate with how much they use it.
Yes. Yeah.
And then
per flight or something.
And then how much as they feel.
Yeah.
It's not cheap up here.
Yeah. I mean, I do. So also, I do a number of flights that for free. For schools, and so I don't necessarily want to pay any more than an ordinary individual. I'm doing them as a business, but I don't want to pay any more than. Yeah, but it can get quite complicated. Anyway, let's start with a donation type scheme and see where we get. I think. Anyway, I'm like preempting all of the
no, it's just getting
investigation.
Nobody's got a massive objection.
No.
Because the short answer is it's not going to get.
It's got to be worth a tenner because just look at what it gives you in comparison with what you're putting out for a flight. £60 in gas and £60 for a balloon.
Well, the balloons will come down in price.
Well, you can try that one tonight. I don't make a big profit on the balloons, I can tell you. it's fairly slim. So there's not a lot to squeeze out of the price of balloons, I can tell you. Right, okay. Sorry. Paul, you carry on. Yeah, please.
Can I steal the microphone?
Oh yeah, sorry.
Just in case.
Yeah. Here we go. I'll give them a start
Good afternoon, everybody. My name's Paul from Durham University, and I'll tell you why we're interested in high-altitude ballooning. So this is probably part 4 of the postprandial somnolescence slot. It's a real thing. Look it up on Google. That's why you feel drowsy. Okay, outline of the talk. I must say I'm going to fly through this. Okay, I've got 50 slides in only 25 minutes. What could possibly go wrong? Okay, I am going to go through it really quickly, but you know the talk is going to be publicly available after today's event. The last slide has got all the details on that you need. Take a photo of the last slide and you're in business, and you can go back and replay it at your leisure. And I'm going to very briefly talk about SuperBit, which is the balloon-borne imaging telescope, which is why Durham's interested in ballooning. SuperBit data recovery, which leads on to our high-altitude balloon toolkit. Everything's underpinned by this. This is SuperBit, so there's an enormous flywheel underneath that stops the telescope from spinning. The telescope sits in basically a boat, so the boat can roll. That's your second degree of freedom. The third degree of freedom is the nod of the telescope. That gives you your 3 axes. So it's not X, Y, Z, it's basically roll, pitch and yaw. So that's Texas. This is an image from Timmins, which is in the middle of Ontario. So this is when we're flying with CSA, the Canadian Space Agency, and in fact, I'm off there tomorrow, which is why I brought an enormous bag with me. This is a big balloon far away. This is a little balloon closer up. We use a little balloon to lift the payload off the ground so that when the big balloon picks it up, it doesn't drag it. Okay? So it's a good way to get your payload up off the ground without dragging it through the trees. We actually release this balloon part way up, and it just goes up on that one, which ends up as a pumpkin the size of a football pitch. Okay, float altitude for us is between 35 and 40 kilometres. It's not quite as cold as some of the weather balloon flights. The pressure's down at about 5 millibar. That puts us above 99.5% of the atmosphere, which means that we don't suffer from, this is a graph of the transmittance of Earth's atmosphere, and the visible bits here, the transmittance goes to 0 in the ultraviolet, which is good for us. It means we don't all have extreme suntans. But in astronomy, we're quite often interested in stuff that's been redshifted from the visible through into the near infrared, and you'll see that there are these big gaps, big holes in the atmospheric transmission that's caused by water absorption. So we'd like to get above the atmosphere so that we can then see stuff that's been redshifted into the near infrared. It's also a heck of a lot cheaper than a space mission. Does it work? Yes, it really does. This is the Eagle Nebula. This is a photograph that was taken in the ultraviolet that we've adjusted for human eyes. But this was a telescope under a balloon. That's not bad, is it? That's really not bad. Okay, that's why Durham are interested. SuperBit will collect hundreds of megabytes of data per night. You are not guaranteed to get your payload back. If you've got time, Google a balloon flight called BLAST, which was one that came down in the Antarctic. The payload got dragged for hundreds of miles because the chute didn't release. They did find the data, but that was about all they found. Everything else was in pieces. So getting your data back down, bearing in mind that this is a long duration flight, it might go on for 3 months. getting that data down in real time is either A, really expensive, or B, impractical. So wouldn't it be nice if we could drop the data off partway through the flight? So if we're launching from Wanaka in New Zealand and the balloon's doing laps of the Earth at 40 degrees south, wouldn't it be nice if we could drop some data off every time it comes back over land? So we're looking at two techniques. The cheap and easy option is data drop capsules. The more logistically difficult and requires better software skills than we've got is autonomous gliders. In terms of data dropping, we have a Raspberry Pi, full-size one, that's equipped with, let's say, 2 terabytes of storage. You know, you can push that to 5 terabytes now in terms of solid-state storage that's relatively affordable. So that's on the back of the board. On the other side of the board is our Iridium electronics powered by the batteries that we know and love. We've got antenna sharing. We've got a U-Blox Max M8Q GPS receiver sharing a single antenna. Up here we've got a servoized archery release, actually a pair of them. So one hangs onto the tether, the other hangs onto the parachute, so that we can release it from the parachute if the safety guys say we can, once it gets stuck in a tree. It's coming down in Canada, it's going to get stuck in a tree. The only connection to the gondola is power, and that connector has been carefully chosen so it has a very, very low extraction force. Because if that sticks, then the whole thing's a write-off. The whole thing weighs in at about 1 kilo, and we're flying 3 of these on Tuesday, we hope. The glider, well, basically Strata Dynamics are doing this now. The highest flight they'd done up till last week was 25 kilometres. They did fly from Timmins last week, and they released at about 32 or 33 kilometres. From what I understand, the flights back to ground went well. It's an autonomous glider. You tell it where you want it to land, and it does the rest. So if it's coming down from 30 kilometres, it might have a down range of about 60 kilometres, let's say. But it means that you can tell the glider to land somewhere convenient, you know, close to a road, for example. That's data recovery. Now, these flights come along once a year, roughly. So if we want to prototype those systems, get them tested in much quicker time, what we did was we developed the high altitude toolkit, where we're taking each of those components, producing them as a standalone design, and then testing them on weather balloon flights. All of our designs are open source. Everything's on GitHub. PCBs, designs, software, Python tools, the lot, but it's all underpinned by Iridium short burst data. Now I know I'm talking to a radio-centric audience here. Iridium's not going to be for everybody, but it is very fit for purpose, as you'll see in a moment. This is version 5 of what we call the Iridium beacon. The Iridium module is actually missing off that. I had to hijack it for something else. Version 5 has separate Iridium and GNSS receivers, antennas. You'll notice that we're using helical antennas because I do prefer those over patch. We started out using patch. I'll show you some images of that, but I'm a convert for helical antennas. There's our Max M8Q again. This is the Iridium transceiver. Underneath is a SAMD 21 Cortex M0 processor as used on the Arduino Zero. It runs off 3 AA cells and weighs in at about 112 grams. We can add a radio board to that, which piggybacks on the top. So this is an LPRS, low power radio. Anyway, the company that makes the ERIC radio processor. So we can put an ERIC 4 or ERIC 9 radio board on there, and then we don't use that to cut communication to the ground. You know, we do that with Iridium, but that then allows us to talk to other bits of the flight train, so that we can, for example, control cut-down devices. So on the data recovery system, we've got 2 serverlized archery releases. The balloon cut-down device, again, it's all on GitHub. That's a standalone board that you can put, it's 115 grams. It's not very light, but it's not bad. You can have that above your parachute in your flight train to let go of the balloon should you want to. It has got a CAM M8 GPS on, GNSS on, so it can be altitude triggered. All of the code actually runs on the ERIC. LPRS give you a software toolkit that lets you reprogram that device. So it's not just a radio transceiver. It can generate PWM for the servo. It's got a UART that you can talk to the GNSS. Basically, we do it all with that one chip. That one runs off a 9-volt battery. Slightly lighter is the Pyrotechnic cut-down version. So again, this is based on the ERIC 4. It runs off 3 AAA batteries, and this is a machined aluminium part where we've got a firework igniter. It's a JTEC electric match that we use to light, I think it's about 0.3 of a gram of smokeless powder. So it's the same amount of powder that you get in a starting pistol blank. Exactly the same amount of powder that you get in a starting pistol blank, which you don't need a firearms certificate for. Okay? So we use the electric match to ignite the smokeless powder. That drives a dowel pin past these pair of holes that your line runs through. That's been flight tested, not a lot, but several times, and it works. But obviously this is for responsible adults. Yeah? The Iridium solar beacon, I've sort of tried to keep the designs evolving as time's gone on. This one runs off 2 power film solar panels. The whole thing, we've got antenna sharing now, like we have on the data recovery system. The whole thing weighs in at 48 grams. So that's a complete solar-powered Iridium tracker. Again, we've got our friend the Max M8. Again, it's running on the SAMD21, the Arduino Zero processor. And it works. We've only flown it 3 times, but it does work. We've got, mine's bigger than yours, Nick. We're using 10 farad supercapacitors. So, taking that design and sort of bringing it full circle, so this is version 5 of the beacon without the radio board. What we've done now is taken that design and turned it into that, where it's 9-volt battery powered. We've dropped the supercapacitors in favour of just a nice step down switch mode regulator. But the whole weight of that system, again including antenna sharing, we're down to 68 grams. So you're kind of getting into small super pressure balloon territory. Again, it's all on GitHub. This is all underpinned by Iridium short burst data. Okay, the Iridium satellite constellation, originally the original satellites went up in about 97. They were famous for producing iridium flares that you could see from the ground. So that was actually a reflection from their main antenna. The satellites have now largely been replaced by Iridium Next satellites, which sadly don't flare. But it's a constellation of satellites in polar orbits, polar, so they cover the whole of the globe. In fact, the coverage at the poles is so good, they have to turn the satellites off. Otherwise, there's just too much coverage at the poles. The thing that's clever about Iridium is if I'm here in the middle of the sea and I want to send a message, I send it up to the satellite that's above me. That satellite relays it to other satellites, and then eventually it gets passed to the one that's closest to the ground station, and then your data gets delivered that way. Okay? But all of this happens in a very small number of seconds. There's not a lot of lag there. But that's really what's novel about Iridium. There are other global data satellite systems, but they're generally in sort of sloped elliptical or equatorial orbits. And you don't get the global coverage. With Iridium, you do. Okay, here's the downside. All right, it's the cost. So this is the short burst data transceiver, little module that was designed by Cambridge consultants in the UK. It's not very big, you know, it's bigger than the big postage stamp, 11.4 grams. It's 115 quid, okay? You have to pay line rental, which is £12 a month, and then the cost per message, it depends how much credit you buy, and it depends who your service provider is, but you're looking at about 10 pence per message, okay? So when you get a software glitch, and this thing starts banging out messages every 10 seconds, which it can, you very soon pick up the phone saying, can you turn it off, please? Yeah, they can do that. How do we track the flight? Well, the Iridium messages can be delivered by email or by HTTP post. Email's easy, obviously. Post needs a server, but you know, we're all comfortable with that. What we've done is we've produced a bunch of Python tools as well, which can automatically, if you go for email, can automatically download the emails for you, strip the attachments, so that's using the Gmail API. You can display the beacon's position, again using Google Python code, using Google static maps, very similar to the tracker. And you can, if you want to share it with the community, there is Python code that will let you upload the balloon's position to Habitat as well. Okay, we've only used that once, but it does work. You know, Iridium, you're not making friends the way you do with radio communication. You know, it's very insular, it's very self-contained, but it's entirely fit for purpose if you're trying to use it in sparsely populated areas. How do we track the flight? The Iridium beacon sends the message up to the Iridium satellite. It gets bounced from satellite to satellite, then comes down to the ground. It goes through your service provider's server and then comes to you either as Gmail or HTTP post. I generally use ROC7, so they're the same people that make the ROC block, which is a standalone Iridium modem, but it's got no intelligence. You know, it doesn't have GPS, it doesn't have a microcontroller. You can add your own, of course. And then that'll display your balloon's position on the Python code. But what's really nice about this system is that your beacon can transmit a message to the satellite to the ground. If you prefix that message with the address of another modem, ROC7 server will automatically kick it back to the satellite, and you can pick it up on another one of these that's just running a slightly different version of the code. So this means you can then track your flight from anywhere. So if you're in the Antarctic, you want to track your flight, control your flight, it's two-way, you can do that. Okay? That's why we've gone down this route. This is what the Python interface looks like with, you know, Google static maps embedded. You can track multiple flights. This is what it looks like if you're online. This is what it can look like if you're offline. And if you are going to be somewhere without internet, you can download these map tiles before you go, and you still get your balloon positions overlaid beautifully on Google static maps. Okay, now then, how am I doing? 5 minutes? I'll try and wind it up. Okay, the flights. The first flight was the University of Bristol SEDS, Sir Richard Meadows flew version 1 of the tracker for us, which was 76 grams worth on a super pressure balloon that they made themselves. Total payload weight, they flew at their own radio tracker, was 91 grams. This flew for 69 days, tracked largely by the radio tracker, because the batteries on the Iridium beacon gave up after 7 days. This was back in 2017, but we did still track the flight. That's what version 1 looked like with the patch antennas. As I say, we've gone now to helical antennas. That was the balloon that Richard and his colleagues made in their kitchen in Bristol. This was the flight path. The beacon did shut down overnight, so the nighttime temperatures are cold enough to drop the battery voltage below about 1.1 volts per cell, so the beacon shuts down overnight, starts transmitting again in the morning, but it went from Bristol out round Spain and Portugal, over Morocco, down the Med, over Iran, Iraq. We were tracking it through China when it went silent and it was heading for this little country over here. But it was just the batteries had gone flat. Through the radio tracker, Richard and his colleagues were able to track it for the rest of the 69 days. It ended up coming down, I think, in Texas. Now then, let me introduce my partner in crime, who is Mark Funk. So Mark and his two sons, Benji and Toby, are balloon enthusiasts based in Switzerland. Now in Switzerland they have a 2 kilo rule. In the UK we have the 2 metre rule. But in Switzerland they can fly payloads of up to 2 kilos without needing aviation authority approval. So that means they can fly a lot more often than we can over here. So it's an ongoing collaboration where we continue to develop and enhance the toolkit. Mark, Benji and Toby take it out and fly it as often as time permits. So this is the 3 solar beacon flights. This one burst and ended up in a field. This one developed a slow leak about here somewhere and ended up in the Med. This one left Switzerland, went over Italy, and also ended up in the Med for mysterious reasons. We don't know quite what happened to that one. So that's the solar beacon flight. Each one of these vertical lines is a fix. 20 flights in Switzerland. Mark lives in Geneva, which is here. So he's done flights in and around Switzerland. He's done flights that have gone up and over the Alps and have landed in Italy. This one was a dual balloon, float balloon, lift balloon flight. The lift balloon was released over here somewhere. It floated for 700 kilometers and ended up in trees just outside Vienna. And we had to go and pull it out of the trees. The flight that's in white there, that was quite an interesting one. We gave that one a very low free lift, so it was a very slow gradual ascent. We lost contact with it here at about 8 o'clock at night when the batteries got too cold. But then it started transmitting again a few hours later from the middle of Lake Constance. So we went back and we looked at we did a retrospective flight prediction. Basically what happened was around the time that it shut down with the cold batteries, the wind, it was still ascending, the wind direction reversed, it went back over here, burst around here somewhere, then came back down and ended up in Lake Constance where it started transmitting again. Okay? We have never lost a flight out of 40. 40 out of 40. One's been nicked, but we've never lost a flight. Okay? No failures.
Gone out to the Med to get ones that...
Oh, no, they're gone forever. Sorry.
Yeah, because that's my...
We know where they were. He's done 5 flights in Greenland, including one that was launched from a ship that landed in the sea. It kept transmitting. I'm going to come back to this one at the very end of the talk. 12 flights in Morocco. He gets around a bit, does Mark, including some very nice, this one over here is actually a 2-ballooner where they tracked each other very closely during the flight, but then diverged a little bit at the landing. So this is Mark, one of his sons. He 3D prints his own sort of neck fill kit, does everything with water cans full of, jerry cans full of water, big cylinders of helium. This is Greenland. This was the launch he did from a ship off the coast of Greenland, so from a ship, and it ditched in the sea, and it kept transmitting. That's how it looks, that's how the flight train looks, camera at the bottom, beacon in the middle, parachute up here, cut down above that, and then the balloon. Quite often comes down in snowy regions in Switzerland. Okay, last 3 slides, 4 slides. These are the images. Okay, so this is an image taken from above the Geneva region looking southwest. So you've got Interlaken here, Interlaken, between the lakes, Lake 1, Lake 2, Interlaken. Over here is Grindelwald, and the Eiger, I think it's that one there. So we're seeing the north face of the Eiger here. This was the same flight looking a little bit further to the south, and that in the centre there is the Matterhorn. Under the cloud over here is Italy. They're not bad photos, are they really? They're not bad. Nearly there. In stark contrast to this area here, which is obviously a little bit browner. Any guesses as to what that is?
Sandstorm.
An enormous great sandstorm, yeah. Yeah, sandstorm that stretches right the way over there. So that's Morocco. This is a really nice one. I don't think I've ever seen the sort of, so we've got the Morocco coastline in here. I don't think I've ever seen the horizon quite as well defined as that. That is a nice one. And again, an awful lot of sand in the upper atmosphere. Very briefly, the double flight that he did in Morocco, 2 balloons launched independently, roughly at the same time, but lucky fellow that he is, they both had cameras, and he was able to photograph one from the other. Which is not bad, is it? That's cool. It's stitched in the sea, it kept transmitting. It doesn't always end well. This is one where the parachute got strangled. The camera hit the dirt. We had to send the climber down to pick up what was left of it. The SD card bounced out, but we got the SD card back, and on it was this image, which is Greenland, Disco. This is Disco, which is an island off the west coast of Greenland. This is what all the fuss is about. This is why Donald Trump wants to buy Greenland, because the brown in the water there is iron. They've got iron running out of the ground. The moon's in the shot, which is really quite nice. Okay, last slide. Take a photo of this one, please, although I think Steve and my dad are going to make the talks publicly available. But if you want to follow up, there's the link. Everything's on GitHub. There is a paper. If you're able to, please cite the paper. Thank you. Have we got time for questions?
No, I don't think so. I think we're going to have to cut it.
Okay.
So.
Catch me at the break if you want to ask me anything.
Yeah.
Okay. Thank you.
You are now, Susan, yeah. Yeah, could you just clip it on, put it in your pocket and clip it on somewhere? Yeah, that's great.
Hi everybody. Hi. My name's Susan Eyre. Those of you who came to the UCAS conference last year might remember me turning up with my presentation asking for help to launch a balloon with the aim of filming cosmic trails at altitude. Well, actually what I wanted to film was the Earth's atmosphere where the activity takes place. I didn't expect to be able to film the cosmic particles at that time. So I just wanted to recap with you quickly on my interests in why I wanted to do this. I've become fascinated by cosmic rays in another project that I was doing called Laboratory of Dark Matters. I've been to visit Bolby Underground Laboratory in the northeast of England with some other artists, and this is where they do dark matter direct detection experiments, and the reason they do it over a kilometre underground is to get away from cosmic rays. So I was very interested in dark matter at the time, but I found that cosmic particles particles would offer me a more tangible contact with outer space. Many of these minute visitors travel across the universe from outside our solar system and even from distant galaxies to enter our world and shower down upon us, colliding with the atmosphere, decaying and powering on to reach the surface of our planet, where they pass through our bodies. Cosmic rays are not visible to us, but their activity can be made visible using a cloud chamber. And this is a really useful way to think about Earth. But because they travel at near the speed of light, they can travel far enough in their short lifespan to be able to reach the Earth and to be seen in the cloud chamber. So they're a very good example of special relativity in action. And some say the invention of the cloud chamber might be the most important piece of experimental equipment in the history of particle physics. It made the study of particles possible. Scottish physicist Charles Wilson won the Nobel Prize for inventing this in 1927. He was actually studying meteorology beginning in about 1894, and he was captured by the beauty of clouds and the strange optical phenomenon of the glory, which is a sort of circular rainbow. He had to climb Ben Nevis to get this sort of view, which you're all very familiar with. So he decided to build a device in the laboratory to try and create clouds without having to climb a mountain to see them. Another cool thing about cosmic rays is they're also key to the use of carbon dating. As they strike atoms of nitrogen in the atmosphere, some turn into carbon-14, which then combines with oxygen to create radioactive carbon dioxide. And this is absorbed by plants, which are then eaten by animals. And when an animal dies, it stops absorbing the carbon-14, and the store starts to decay, making it possible to estimate the time of death. So, as I mentioned last year, I've been part of an artist residency programme at Alan Head's Contemporary Arts, based in Northumberland. It's the only arts venue in the UK with an astronomical observatory. In 2018, the project Beyond, we were exploring the mysteries of the universe through the lens of art and science, and this became a project called Continuum, which went into 2019 and took a more speculative approach, engaging more with science fiction and imagined possibilities. It was about that time when I came along last year to seek help and advice from the group, and enjoyed my first launch experience. And from some of the conversations at the time, I was encouraged to think that it might actually be possible to launch a cloud chamber in the payload and film particle activity at altitude. After meeting everyone and seeing the balloon launch, I've been making lists and reading Dave's how-to tips and following the email advice topics, but I was still struggling to make progress, as I found a lot of the advice given to me in a language I was unfamiliar with. And so, especially with the tracking and the radius, so I wasn't getting very far, but I was lucky enough to meet someone who worked at Imperial College and was chatting about this, and they thought they could put me in touch with colleagues who would be able to help. So in November, I was introduced to the senior lecturer in spacecraft engineering, Dr. Aaron Knoll, who offered to supervise some students from the Imperial College Space Society, if any would be interested in the project. And from his perspective, it gave the students an opportunity to work to a real-time brief, and I would provide the funding and hopefully get video that I wanted for the exhibition. So Medad, Senna and Roman came forward, and despite all their own work commitments and exams in the new year, they met up regularly to construct the components required. I had anticipated a public event at Alan Head's, arranged around the launch of the balloon, but even if that were possible to plan for, it was probably too risky, it turned out, as the coast was annoyingly close and any prevailing winds would have put the payload out to sea. So it was also a bit far to expect the students in London to travel, and so Medad found some more suitable locations and put in the necessary requests. So chamber that I put together during the Laboratory of Dark Matter project was made from a plastic fish tank, inverted over a thick anodised aluminium plate with a milled groove for the tank to sit in to hold alcohol to create an airtight seal. And then thick felt is attached to the inside top of the tank and soaked in isopropyl alcohol before each session. And the aluminium plate sits on dry ice, and a hot water bottle is placed on top, and that helps the alcohol vapour to form. The air inside the tank needs to become supersaturated, so when a particle passes through, the alcohol condenses onto the particle, and that creates the beautiful trails that we see. And this setup achieves very good results, with lots of trails visible, and runs for about 2 hours. I also run workshops allowing people to see particle trails using very simple materials like plastic beakers and tin foil tray. And the students needed to replicate this apparatus to make it able to withstand the air pressure, temperature and turbulence of a high altitude flight. So they had a go with the workshop kit to view particles. So they made their own design for a chamber using acrylic sheets bolted to an aluminium base and lined on top and 3 sides with felt. And the chamber was glued and heat sealed to be airtight to withstand the decreasing pressure outside. So this is the meetings we had, the various components that they were designing. And a heat pad was fixed to the top of the chamber, and there was some talk of using the outside temperature outside the box to chill the base, but I'm not sure that that would have been cold enough. So the timescale for the project had been determined by the upcoming exhibition that I'd hoped to make work for midsummer in June, and this wasn't great timing for the students because that was when their end of year exams were happening, so they had a lot of other things on at the time. And so as time went on, it hadn't really been possible to carry out any tests on the chamber. And with the launch date pre-booked with the CAA upon us, and just 3 days' notice, the team decided that we had to go ahead, ready or not. There was a mild panic when we discovered that helium wasn't so readily available, but we did find a supplier to deliver in time. So it was all hands on deck, and I was charged with making the connector for the helium cylinder, following the fill tube guidelines, very useful on the wiki site, so I did get to do a little bit of practical stuff towards this. And then the evening before the launch, I received an email. Disaster had struck. So not wanting to disappoint me, they decided to work into the night to make an emergency replacement. So we decided to go ahead with the launch anyway, though I had said, it was fine, let's just concentrate on getting some film from it. But so they made a replacement, and we set out the next morning to Oakley Airfield. We were given permission by Tom Baxter, the landowner there. And we have Steve Hyde to thank for his invaluable help on the day. We also have Richard Ibbotson to help with tracking. We had 2 payload boxes. In the end, the cloud chamber in one box with dry ice, didn't therefore get all the video that was hoping for. Also, the camera that was pointing at the cloud chain had shifted even before launch, and so we will never know if any particles were made visible. So this activity at altitude remains unseen. Due to the unpredictability of high altitude ballooning and the need to have some work ready for the exhibition, I had devised work which could incorporate whatever outcomes we'd have from the balloon. Possibilities, and planned to install a wormhole. As we said, no, black holes were once thought to be science fiction, but have since been proved to exist, and this could also be the case with wormholes, though there are a few more obstacles to overcome. Travel across space by means of a wormhole. So first of all, you need vast amounts of negative energy. Climate. Very short supply. The risks and obstacles include creating enough negative energy to open the wormhole mouth wide enough to weaken gravitational tidal forces, which would rip travellers apart. You have to keep it from collapsing so that travellers are not indefinitely trapped inside, and you have to exceed the speed of light and avoid incineration from deadly high radiation. So I was privileged to be allowed to install the work which was called Aeratus, which translates as unseen, in the 200-year-old blacksmith's forge in the village at Allen Heads. During the midsummer weekend, visitors were invited to burn offerings of negative energy to power the wormhole. They were given specially prepared tokens that would burn with coloured flames, and they could write or draw outpourings of their negative energy onto the paper, and we burnt them in the forge fire, which would release the negative energy to power the wormhole, which was installed appropriately upstairs above the fire. Once they went upstairs, then they could go through the portal curtain and into the video installation, which was 3 circular films with imagery referencing theories of possible tiny wormholes connecting all points in space, cosmic strings, space foam, phenomena related to the experience of travelling through space, and offering an alternative perspective on the world. So as well as footage from the balloon, I put an endoscope down rabbit holes, a microscope pushed into fibres and foam, used the bare branches of trees to reflect the branching decay of particles, and I had Steve Randall and Steve Hyde to thank for kindly allowing me to use footage that we were unable to get of the Earth against black space. So after a cathartic burning of negative energy and seeing the beauty and mystery of the Earth, hopefully visitors would leave feeling positively charged. Finally, coming out on it. Finally, in the payload was also a black and white 35mm film, which went over 35 kilometres up to near space. So I don't know if you can see them on there, but on this monitor slightly, there's some faint white dots. Yeah. And I don't know if these are evidence of particle activity or just noise, general noise in the crystals of the photoemulsion, but I like to believe that I do have some record of particle activity from our dawn. There wasn't any technical information really there about the launch, but if you had any questions about what we actually did, then I'm sure Medad would be able to answer anything about about the tracking and that side of it. But yeah, it's been a really good experience, so thank you for listening.
go for it. We'll sort out
just let me know.
We'll sort out the timing.
Right.
We're drifting a bit, but I think we've got more time at the end now.
Okay.
We're not doing the balloon launch. So.
Right. So just let me know when.
Yeah. Okay.
Okay.
Go 15 minutes, I think.
Right. Hello. Good afternoon, everybody. My name is Medad, and I do this project with Richard Ibbotson, and part of the Imperial College Space Society, to send a balloon around the world. We are not the first to attempt to do this, and in fact quite a few people have successfully flown their balloon around the world, but we want to do it as well. We build our own trackers, and there's a lot of fun that goes into this whole build process, really. And so just quick introduction to the Imperial College Space Society. It's a society which of generally space enthusiasts, and we do space-related projects. We do rockets, we do rovers, visit space agency headquarters and institutions, and so some of us take part in competitions for rovers, satellites, and of course the high altitude ballooning as well. And so over the course of the last year, Space Society have done a total of about 14 balloon launches of the small variety, and we normally launch from up the road at Wormwood Scrubs, which is a humongous field. And so this was actually from our first launch in the field, so we have all the kit on the field. We filled the balloons there, but now we have changed the way we do things a bit. But it's a very good field in London itself, where we launch, and we do not, and the balloons are small, so within CAA's requirements. So I just will show a short clip of one of our launches. This is IC Space 13 that went to Poland. And I must comment that this was a very calm day, but we have launched in days where planes couldn't land at Heathrow. But we did lose one balloon on a tree, that's it, so not too bad. So a quick overview of the balloon. So we have, we want to go around the world, so we have built these prototype trackers, low-cost trackers. The whole launch cost about £25, easy to build using off-the-shelf parts, low weight between 15 to 25 grams, and the longest times we have seen is 12 hours lifetime of continuous transmissions. And so the range of these, we transmit using the UK has style RTTY transmission, and so the range for where it can be picked up is all the way to Netherlands, Poland, and France, where they listen in using to that protocol. So we've done 14 launches, and some of the objectives we wanted was we should be able to survive at the cold. So the coldest we have seen is negative 35 degrees Celsius, and we had to conform code some the trackers after we realized I think this moisture is damaging them. I'm going to pass around one of the trackers which we flew it on the cloud chamber, but it's the same design. So it's slightly sturdier and heavier than the ones we fly on Pico balloons. We have not recovered any of those. So all our flights on the map at the moment, as you see, the longest flight went to Poland, I think about 2 weeks ago, and several flights to the Netherlands and Belgium to Europe. Almost all the flights, no, in fact, one flight landed in the Netherlands, but the rest just ran out of battery. So what we have been improved, and yeah, so over the time we have figured out that there are various things we can do to improve the battery life and lifetime in the air. Okay, so the main components we have on board is all off-the-shelf parts. The top one is a HC12 radio and processor module, GPS receiver, 3.3 volt boost converter, and a lithium AAA cell, and we integrate it all into a piece of foam. The components alone just weigh about 15 grams alone, but we do some modifications. Everything is done using freely available software. So this is just the components on the polystyrene piece. We use very low density polystyrene. So I'll let Richard continue.
I'll come over there for that.
Yes.
So which move slides?
Next.
Okay, so simple design objectives, a £15 tracker, 15 grams, and a short time scale to actually develop the trackers. So where do we start? Well, AliExpress is a place I normally start for low-cost devices. And so we found this radio, this HC12 radio on AliExpress at a price which was cheaper than buying the radio chips from Bowser or DigiKey. It's a Scilabs SI4463, a very common radio transceiver with a 433 megahertz transmit-receive path based on pretty much the datasheet design. It's got an STM8 processor, only about 8K of flash, but that's not really a problem for what we're doing. Serial TTL interface, about 1.2 grams in weight. Quiescent current, not particularly good. It's got a regulator on there which we don't need, but it's actually taking quiescent current. And when it's transmitting, it's about 20 milliamps that we're taking. Obviously, with something you're buying off the shelf, which is really a remote control type transceiver, there's bound to be some limitations. There's no crystal on the processor, which does have an impact if you're doing RTTY, and so the serial interface is not actually crystal control. So as the temperature goes up and down, obviously the processor speed clock will change. The processor is actually quite good on that, but we were aware of that, and we knew that the regulator would give us quiescent current, and the level shifters gave us that as well, although they were not used. We had some surprises with it. The first ones we plugged in, we reprogrammed, they worked just fine. But then the next batch that we bought, they changed the type of processor from a SIC outline to a QFN outline. They changed the radio, in fact, from a Scilabs 4463 to a 4438, which it is pin compatible, it's radio compatible, but it's a 433 only radio. So that wasn't a problem. Although as they did those two changes, they also changed the pin out of the actual board that they were using, so we had to actually change the software to actually allow for that. They just swapped a couple of pins over, but it was just frustrating. One of the problems we've had from the beginning with these is they have very poor quality crystals on them, and if you're doing RTTY, you need pretty tight control of the frequency. They were drifting as they warmed up, even when we weren't at low temperature, they were drifting as we warmed up. We did change those for decent quality crystals, that was slightly better, but in the end we had to add a temperature compensated crystal oscillator to it to actually get the stability that we wanted for the RTTY and the FSK. And also one of the surprises on the last batch we bought, they just didn't work. And when we actually went into the design, there was a track missing on the PCB, so they didn't actually work with their original code. They would never have worked, and they were obviously shifting thousands out through the door, which could never work. There was a track missing, that there was no TX bias voltage going to the transmitter, so they would never have worked in any mode. So it gives you some idea of some of the risks of buying Chinese stuff, that they're clones of clones sometimes, and you can never be quite sure what you get. So what we had to do is at the top of there's the 30 meg crystal that they come with. We actually take that off. We add, you can see here, we actually tombstone three 0603 components underneath on the crystal pads underneath, then put the TCXO on top and power it off an unused output from the processor to turn that on and off. It's obviously one of the objectives was to make it very simple that anybody could build, and that modification is a little bit tricky. It's something that most people can do with a pair of tweezers and an eyeglass, but just getting the wire onto the QFN chip is a little bit difficult. So slight miss on the objectives there. For the GPS, yeah, back to AliExpress. These are the GNSS modules we've been using. They're GPS and GLONASS. They're genuine U-Blocks M8 chips on there. They've got a low noise amplifier and a SAW filter built in. They've got backup capacitors, flash memory, T60. So pretty much everything we want. When we first started buying them, they were, I think, only about £5 or £6. They've gone up in price recently. Yeah, a very competent M8 radio at a reasonable price. We knew there were some limitations. They've got a couple of LEDs on there, one of which we can turn off if we go into low power mode, one of which is on all the time. There's no power control on the low noise amplifier and the oscillator. So we do have quite a high, that quiescent current there is 12 milliamps. That's now down to about 7 or 8 because we take the LEDs off. And there's a regulator there that's unnecessary. We're still not 100% in terms of performance, but we think that's more to do with the interaction of the 433 radio with the GPS module. We have had the number of satellites is not always consistent, and we have had a few times when we've lost communication with the GPS. But you know, at that sort of price for a complete module was fairly good. So again, what we do is we take the shielding off. The module, remove the puck antenna. So by doing that, we go down from 7.5 grams to 1.5 grams, and then we just add a guitar wire antenna and put conformal coating on to waterproof it. Obviously, the power supply, the classic Energizer AAA lithium primary cell. We solder the wires directly onto the battery rather than use a battery holder because that was adding a gram or something like that. We tried a couple of different boost converters to take the battery voltage up to 3.3 volt. These are some Chinese ones that we got. These are like, I don't know, 40p or something like that. Although the quality of those was not good. A number of them had broken inductors, and also the IC they use is not very good at low voltages to give the peak currents. And so the one at the top is part of a previous project we had using an MCP 1640 boost regulator, and they seem to be pretty good. So by putting those basic components together, we're able to put together a tracker. The programming on the back of the HC12 module, there's a couple of programming pins there which allow us to do the downloaded code and also to do the debugging. We use the IAR embedded workbench for the STMA. There is a free version of that for limited size code, so it's only 8K, but as I said, the processor only has 8K of flash, so it didn't make any difference. So it's actually a very nice development environment, free. We actually do the programming with an ST-Link module. This is a programmer for both STM8s and STM32s. These are, again, clones. They're about £3 to buy. And you know, they'll do the programming. They'll also do line-by-line debugging. So it's a full-function debugger. So it is very impressive. We've made a programming clip, just a clip, a 3D print clip with pogo pins. It just clips on the back of the board, allows us to program them up, either on the bench or in the field. The software, mostly developed by Medad, based on existing source code. which I'm sure people in this room will probably recognise because they probably wrote some of it. So
3D printed, or the frame was, but it's too heavy. But it adds 5 grams, and every gram matters with these lightweight balloon trackers. So we ditched that for now. And two of our flights disappeared or stopped transmitting around the same region in Belgium. So, and we felt that there's no reason for it to just stop unless something happened to it. And we think maybe it's the moisture in the air. Maybe it went to the clouds and messed up the electronics. So nowadays we conform code all the electronics ahead of time. And so we launched them on small party balloons, something like that, off-the-shelf Qualitex 36-inch party balloons. It's the mainstay for most people who have done the small balloons, at least initially tried those. I've got some of the Dutch and Swedish balloonists recommend this AliExpress balloon. It strikes me as some sort of multi-layer 36-inch film, but I've not tried it. But don't know if anybody has experience with this. It's the same size as the Qualitex one, and also much cheaper. And so when we fill the balloon, what we do is we keep the valve. We weigh down the tracker with 1 gram weights of solder, and then weigh down, let's say, 2 grams, and then once it reaches starts hovering, we know that the net is 2 grams. It's very useful to do it that way. In our recent flights, on advice from some folks in the IRC chat, with the Qualitex balloons, we have a self-sealing valve, but I think that fails at high pressure. So the recommended way is to stuff glue down the valve, permanently seal it, and it really has helped. I mean, you've seen it. Usually we burst at about 7,000 meters, but it's going up pretty well. We tried impulse sealing the valves with one of these sealers, but we found that it seems to induce leaks where we seal it. So the tiny holes that form and goes up and comes back down too early. So this is a setup in field park bench, antenna pointing up, towards roughly laptop connected. Yeah, so with these prototype flights, I would call it prototype flight because they're really off-the-shelf components. We have kept it within a low cost. We made it really light, or I think it's as light as it gets really with the off-the-shelf parts, non-customized parts. Done 14 launches, but now we've come to the point where really it's hard to improve it any further. But in the process, we are very fortunate to have spoken with lots of people. People have turned up for our launch. In fact, some folks that even here in this room have unannounced turned up for our launches in London. So we are grateful for your help. And now, next, we are currently building the Mark II with a custom circuit board, and we'll hopefully target is to launch within get around the world in the next 2 academic terms. That ends in May next year. And very excited about this. We've done a schematic, and the plan is to use LoRa and the Things network, so the LoRa WAN network to get all the information to us. And there are base stations all over the world, and I think it should be possible. So thank you.
Questions? Okay, we're going to have a short break, about 10 minutes. Sorry, okay, carry on.
You said you had problems with when they changed the SI chip to the 468, right?
We were, yeah, the original one was the 4463.
Yeah.
The 4438 is I think it's a slightly lower cost version that's been done for meter reading, and so it's sort of pin compatible, but just doesn't have the same bandwidth. So it's something like
438 or 468, I think it is.
No, 4438 it is.
Okay, then you have the different one.
So it is. It's just a limited bandwidth version of the 6.3.
Because I had initially the
No, it is actually pin compatible and software compatible.
Yeah.
It's just a limited frequency range. That's the only difference. Although the actual output power is slightly higher, so we have to actually make a small change to the output power level.
Okay, so we're going to break now for about 10 minutes, say. So come back at 15:50, so call it 10 to 4.
Okay, had to think there. Good afternoon. I am Andrew Mulholland. I'm a school teacher, and apparently some of my students have turned up today at the back. Do you not get a cheer? You said you were going to cheer me on. I was more talking to the school students, but okay. Radiosondes. There's a bit of argument about how you pronounce this word. I'm going to go with radiosondes. If I'm offending anybody by the way I'm saying it, too bad. At this point, I didn't get to see the talk earlier on, the AutoRx talk, because I work in a boarding school and I was teaching this morning. But I'm assuming you all know what this is at this point, an RS-41. This is a primary school that I was doing a lunch with back in June. Very enthusiastic bunch of kids. This was over in Northern Ireland. Phil was there. Phil gave us a wave. He helped us with the filling bit and everything like that. These kids spent, I think it must have been 4 or 5 months. Every Tuesday morning I was in with them and we were working on this launch. They're very excited and they were year 6 kids. This was a pretty big deal for them. They filled a balloon. We made a video and I'm just going to show a little bit of it. But they were all very excited. They had a countdown. You know, this is a pretty big deal for them. It's a rural school. They don't get to do much science or tech stuff. They spent a long time working on this project, right? You know, a lot of hours of them working on this project. Big deal for them. Northern Ireland's not a very big place, so this was a big deal for them. And then, at this point, the Pie in the Sky tracker failed.
It launches about 6 AM in the morning, goes up to its maximum height of about anybody. So you have an approximate location. Anything else that they want think is all the way up.
I don't think we ever, it was kind of the end of
sharing the screen.
Yeah, this has gone off. The streaming's gone off, and I can't connect from my PC. And right, anyway, let's just present something. So this is a joint presentation with myself and Dave. A couple of years ago, oh, actually I must be wearing this, I think, most of the time. A couple of years ago, Hawaii, I think how you're supposed to say it, introduced a new range of balloons called NSL, and got quite interested because, being interested in altitude, they said that they could realise a height of 45 kilometres or even 50 kilometres. Which, hey, another 5 kilometres onto what we've done. So it's a range of balloons, and the number at the end basically means the height that they sort of expect them to achieve with, I think, a standard payload weight. I asked them what NSL stood for the other day, but I framed it like, does NSL stand for Near Space Line? And they said yes.
I think it's after our flights and no slugging the lap.
No, could be, yeah. So there's a couple of features that make them unique. One is at the sheer size of the balloon. So it's an 8,000 gram balloon. I mean, the nearest one I know is 4,000 grams, and that's produced by Totex. They claim about the same burst altitude, but this must be a lot higher, because if you can't achieve that altitude with a standard of 15. So the other thing that's interesting about them, as you see from this photograph, is it's a balloon inside a balloon design. So they take a big balloon and they stuff it inside a small balloon. And this isn't a method of getting higher in general, it's just a method of constraining the size of the big balloon to be small when you launch it. So you can fill the balloon and you can get it out through standard filling station doors and then launch it. So there's a picture in China, I think, of them trying one. The other thing that's interesting about them is they have pre-fitted a valve in the neck, because I think it's to do with the fact that they've got a neck inside a neck, so they want to have like a pre-fitted valve so that the whole thing is standard. I mean, the valves are, there's one on the left-hand side here is pretty standard on Totex balloons if you're auto launching them. So actually, I think the Radiosonde chasers probably find quite a few of those. But the one on this one here, the bigger one, is what you get with the NSL 45. So I spoke to Dave about this, and he was interested too. So that's when Team Pushing the Edge was formed. Envelope. Pushing the Envelope. I said that before as well. So yeah, Pushing the Envelope was formed. So the first thing that we did, when we were preparing for our first flight, was I made a filling attachment to plug in the bottom of the balloon to allow us to fit it, so we didn't have to modify it. So I made that, and then we went down to Dave's, and this was our first.
Is this the video?
This is the video, Dave. This is our first attempt. You notice that I'm wearing a matching two-piece. No, it's a flame retardant. Overall,
some funny music.
Yeah. So let's see. We into what screen? Yes, here we go. So this is the fill. August, was it August last year?
Somewhere around there.
Yeah. So
notice all the cylinders.
Yeah, lots of cylinders.
They're about 5 and a bit.
No. So
that's about 10.
This is a good point to stop it. So
I wish we had.
So one of the things that you'll notice about this balloon is it's got a heck of a lot of the internal balloon pushed against the outside balloon, and this basically makes it off balance. And we're normally used to the balloon sort of like going up from the neck. Well, this basically makes it awkward. what you can do is once it's inflated a bit and upright, it's sort of like push the envelope and a bit of it will fall down, and that balances it a bit. But it's still, we're not used to it. It's an unusual thing. But anyway, let's go on from this point. So don't bear in mind.
Should we mention the cost at this point?
Yeah. Okay then. So
it's not cheap.
It's not cheap. I mean, we're talking over £1,000. Well over £1,000 for a balloon. Oh, there we go. So yeah, it's worth watching that again. Nice duck and roll, Dave.
So go back a bit further to see where the helper was helping.
Well, I could go. Yeah. So would you want to go in?
Let's go back to where Greg was.
Oh yeah. Okay. So yeah. Let's wind back a bit then.
Yeah, okay.
So what we've got a combination of about 3 things that went wrong really. One is
a bit further.
Yeah, I can't. This thing's in the way.
Just click on the
exit. No.
You've got hydrogen or helium in this?
Hydrogen. Yeah.
Hence the red.
Hence the red. Yeah.
Hence the flame retardant soup. I can't get it to do it. Anyway, so we'll just have to go forward.
Okay.
But what the sequences of events were, we were filling the balloon. I was reasonably confident about wind directions coming, away from pushing it away from the fence. The gent that was looking after holding it back went off to get his camera, and at that instant, it decided it was going to lift off the mat.
And a bit of wind helped it as well, I think.
Yeah, the wind came in from a different direction. Basically, it suddenly came from a direction we weren't expecting.
But anyway, watch my roll.
Yeah, watch these. Okay, let's. So you get the bang. Another go at that. Here's another laugh.
Yeah, you still got to reuse that.
I thought it was coming down on top of it, I think. But to be honest, I'm not sure. All I can do.
Dave sums it up in a minute when we turn the gas off, I think. Don't get near it.
Yeah.
Right. So, yeah, that was entertaining.
So we did actually fly a balloon that day, but obviously not that way. Neither of those ones. I mean, when it went, I thought, I hope it's the outside one, and the inside one's still okay.
So, for that little escapade, nil point.
Was the inner balloon okay?
So, no, that was what I was hoping.
Yeah.
In fact, I was kind of trying to see if I could save the inner balloon, but they both went so.
I think the only thing that we got out of that was to see how big the inner balloon was, because it sort of like shot out and stood up. But
I mean, at least we had the remnants of the way everything afterwards, so we knew a bit more about them. But that's an expensive way of finding out.
Yeah.
You can't use a bicycle
It was well versed.
Yeah. Gorilla glue, gorilla tape.
So, basically about a month later, Mark Deegan decided to launch on the same type of balloon from North Wales. So we watched this flight with great interest to see whether or not we break the record.
We were expecting to see in the assets, you imagine this balloon that's round, and then when the other one goes, it's going to be a long, kind of tip-up shaped thing. So I was expecting the asset rate to kind of halt for a moment and then go back to normal. But it dropped. So the unit actually, on the telemetry actually came down.
So that's the ascent rate there, and you can see this huge spike. This is where it dropped at 11 kilometres, 11.5 kilometres. So we assume that's where the outer balloon burst. And but otherwise, the ascent rate is pretty constant. So because the balloon is spherical almost the entire flight, because the inner balloon constrains it, the outer balloon constrains it in the early parts of the flight because it's full, and then when that bursts, immediately the inner balloon inflates to spherical as well if you do the calculations. So it's spherical all the way up. It's just constrained a bit, to start with, and when it bursts, it immediately expands to the film. So yeah, more or less more or less constant descent rate all the way up. There's the descent rate graph. Now you can see what happened with this slide is it floated. Basically, the descent rate was too slow, and it just ended up floating and not achieving its maximum altitude. And there's sort of to get the maximum altitude out of one of these types of balloons is you need, if you put too little gas in, you will get exactly what happens here. It will end up going into a float and not achieving maximum altitude. If you put too much gas in, it will go up too fast and burst early and not achieve its maximum altitude. So you need to get in between those two, and you need to find that exact point to get the maximum out of it. So we looked at this graph and calculated how much extra gas we thought we would need in order to achieve that perfect high altitude shot, based on our experiences with the Hawaii 1600 gram balloon. You know, we can see this type of profile on 1600 gram balloons and just look to see how much faster we needed to send it up. So we got that information really out of Mark's slide. So here's Mark's fill video, and notice he's going to shake the balloon to redistribute the weight, so he didn't really have the same problem as us. So one of the interesting things was we saw he had 2 bottles of water on here for measuring the amount of lift. Don't know what that noise is. Scary.
He's taken the fill out.
He has taken the valves out, and the shaking, you can see, is now shaking the inner balloon down a bit. So get it so it's a bit more, you know. And the other thing we worked out was he used 2 entire cylinders of gas.
So that's about just under the 11.
Yeah. So we knew how much gas he'd used, how much negative he was going.
You see there, it's not shiny.
Yeah. And that's after a lot of work.
Where the hell is his website?
Yeah.
with hydrogen?
There's no way on the website. Anyway.
Well, yeah, the only thing I'll say is that you got successful launch.
Yes. Well, no, not that we're bitter.
Not that we were bitter. So about a month after that, no, actually 2 weeks, I think it was. Okay. So we had a bit of a snoop around the internet. We found some information, I think, on IRC, some information about the size of the bottles and how much, how big they were, and we sort of like worked it all out and thought, right, okay, we know where we're aiming for now in terms of fill. So here comes PTE2. As I say, this is probably one of the most interesting. This is the most interesting one out of ours. Just before we get on to the video and stuff, things to note here is that I put up a windshield. You'll see that in the video in a minute. I used that originally for another flight, and it was really quite useful, even with, because it's such a big balloon, even with trees, it's still not enough to sort of like shield it from the wind. So we've got a windshield as well. And again, we're still struggling with it being top heavy. I think because I was Hawaii's best customer for these balloons by far, they sent me one of these fill attachments for it. So this is like a specific thing. It is 1.5 kilos of brass, solid brass. Don't ask me quite why, but anyway, brilliant. So it attaches. You push that tab in, and it sort of like locks the neck in place. So we was using that for this fill. So this is a time lapse of the fill. So it's just so you'll see that's actually 2.5 meters the side that windbreak. And it'll give you an idea because of the size of the balloon. Again, you can see it's going to be offsetting. You can see all this mass at the bottom, which must be as they feed the balloon inside the other one, it all drops to the bottom.
I don't do much, do I?
You were holding it and making sure it didn't go away. But I'm behind there somewhere with this attachment, trying to fill it, and real trouble was that because it was like going down, you couldn't just put the fill thing on the ground, which I think is what was originally intended, because it would sort of like cut the flow off. So I was having to hold it up, as well as struggle with this balloon that's off centre. But anyway, it gives you a bit of an idea about the size of the balloon. But the actual launch is pretty quick at the end of this. Sort of like, the good thing about that fill valve is you can literally attach everything to it and then go. You know, just pull the tab off and off it goes.
we thought it was going so well.
So we had two different trackers on this. One Dave made, one I made. One was PicBase, one was Raspberry Pi. I had an LAT, I think.
Yeah, we had, because the manufacturer says 45, maybe 50 kilometres, and the U-box craps out at 50. So I bought an LAT, which is 80 kilometres as long as you put it into a balloon mode. So we had, I just used that one with the Pi. So the Pi had that, and Steve had the U-box on the So what can go wrong?
What can possibly go wrong? Two trackers, different people. Right, Dave, do you want to take over?
Yes.
Just give that one to them.
Yeah.
You have to wonder, don't you, sometimes?
You need experienced people to do that. Oops. So yeah, so it stopped. So why did it stop? Let's have a look. That's an unusual shot to be seeing from a tracker that's supposed to be 10 metres, 15 metres below a balloon. So basically what happened was the weight of the balloon made it tip up, so the filling valve was near the top. When I tied my tracker on, I just kind of wrapped it around with the nylon thread. I should have taken it down and kept it solid, but basically we think it just kept bouncing against the balloon on the way up. So you get lovely shots like that, but it's about the halfway point on the balloon probably. On that one. Now that's the. That's to get that in. So mine then, I think it was about 30 something kilometres. Mine stopped altogether. So we're pretty sure it got broken apart and fell. It did fall off. We know later it fell off. Steve's tracker was still working, so that was okay. Except that then was it by then or
it started at 20 kilometres.
20. So unfortunately, Steve's was saying, "I'm not here. I'm here," and the altitude was locked as well, if I remember rightly.
That's right.
So we didn't have any updates on that. So at this point, how are we going to find that balloon? Well, let's see. So that was the prediction we had. So yeah, so 35 kilometres was the last altitude for mine. So that, if you like, is one data point. Yeah. So we all run our predictions before the flight, and they're within 5 miles radius roughly of where it's going to land. I wouldn't like to try and search a 5-mile radius area, not knowing where the balloon is in that. So, but we can do better. So my first thought was we can, if we wait till it bursts, you can hear that, especially on RTTY. You'll hear and then you'll hear kind of shh, 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 as the thing's rotating as it comes down. So that would give us the timestamp of the burst. Oh yeah, I should have done this first. I was intent on finding this thing. So yeah, so we have time up to 35. We can listen for the burst and get a timestamp for that. So we've got timestamp and altitude for the last point. We've got timestamp, we won't know the altitude, we don't think. But that at least will give us, we can calculate the average ascent rate up to then. We can estimate the burst altitude, and then we can assume it's landing at 5 metres per second and see how that goes. So we can do on that third one there, we can fit the rest of the ascent. If we listen for the loss of signal, so I went on IRC and asked everyone, when for at least the guys close to the landing point, tell me when you lose the signal, because you're going to lose it 300 metres above the ground. I can extrapolate from that easily enough. And that will give me a timestamp and obviously an altitude for the end. so I can fill in the whole thing to some extent. Then we had a moment of luck where Steve's tracker, now Steve generally you send when he sends a string, telemetry string, he'll send the highest altitude since the previous one rather than the current. And the idea of that is if you send the telemetry string just after burst, you'll send the burst altitude rather than the current altitude, which would be a bit lower. And Steve's, I don't know what happened, and Steve doesn't know what happened, but it magically woke up and said, I hit 45,289 meters. Now we're not going to put that in the record because that's just a tracker claiming it. But now we had not only the burst time, but we had the burst altitude. So I could fit those into the predictor and plot the ascent rate with some precision. And of course we had the landing time. By then we hadn't, but later on we had the landing time as well. So we had last known position for my tracker. We had the burst time by listening to it. So I just wrote down a bit of paper after listening to the radio. We had the burst altitude as well, and we had loss of signal timestamp there. So I went back to the hub, just kept fiddling with. I put the burst altitude in. So you start with the current altitude there. I put in the burst altitude. I adjusted the ascent rate until the timing worked out for the burst, and then adjusted the landing speed until that matched as well. So basically I filled in the rest of that plot. And that's what we got. So it's better than nothing. So Steve had another flight to do. So me and my wife got in the car and aimed for that. And I expected, so if we put a prediction in at the beginning of a flight based on what you think the field's going to be, you'll be within a few miles of the landing. And I thought, well, it's going to be a bit better than that, but I don't know how much better. Anyway, so we got there. There's a petrol station just here, and as we pulled into the petrol station, knowing that that's the prediction, and I thought, well, we're going to have to drive around probably an hour, drive around all the roads nearby. We pulled into the petrol station, and the radio started working. That's a bit of luck. So then the next thing was to try and decode the transmission. Is the tracker working now? No, it's not. It's still sending the same data it was sending an hour ago. So the next thing is to get Yagi aerial out. Okay, let's jump again. Get Yagi aerial out and do some direction finding. So from here, I knew it was that away roughly, and then we drove up to around. There's a railway crossing there, so we parked up there, and we got a direction roughly this way as well. The issue was that we should have a satellite image. That's all trees, all around there.
Yeah, on the side.
And so it was about
there somewhere. Yeah.
So and how to get there? So first off, I went from here. Just walked along. There's trees there. Get in here. I walked around the trees, and the problem is, everywhere you point, you get a signal because the trees are bouncing this signal around everywhere. So we couldn't find the tracker. So we went round this side and came down the railway line on this side. And again, pointing, you get points where it must be right in front of it. It's really bouncing strong. The problem is, those railway tracks make really good reflectors. So we had no idea, to be honest. I thought it must be on the railway track, so I went through the brambles and stuff, ripped my jeans apart, couldn't find it on the track. And eventually it was getting dark and I gave up. And then Steve went back the next morning. Now the problem is, I said to Steve, it's there. So Steve did the same as I did and got the same results.
Yeah.
And it wasn't there.
It's got to be in those trees.
It's got to be.
It's got to be in the trees.
It's got to be in the trees.
Spent hours.
Yeah. And at one point, actually, I was walking on here, and I thought, maybe it's over here somewhere, and I just aimed the other way, and got a decent signal, but I couldn't see the thing. But the problem was,
it wasn't as strong that way.
No, it wasn't as strong. It was much stronger this way.
Yeah.
The reason it wasn't as strong that way is because there's a slight incline here, and it was actually over the brow of a very slight hill. So looking at it directly had a weak signal. Looking at it the other way, it's bouncing off the trees above, over my head. So it lied to both of us. yeah, it's one for the brain cells. That one is. Steve, so you can talk about this bit.
Do you want to get the microphone back? So I went there the next day, as Dave said, and had a look round, and because I was sort of like predisposed to Dave's solution, I think, I assumed, it's in the same position. I'd taken my drone and flew it about, and but looking on a little screen, you don't see things like a little white dot in the middle of the field. You know, no winds. We were walking. I was walking around in my socks on this ground sheet to make sure it was absolutely, spotless. Once we got on the ground sheet, we wouldn't come off it. And it was a dream. I mean, the for the size, of the balloon, it was a dream filled really. There was no struggling against the wind. So here we go. Sort of like a little bit of wind there, but they've held it back with gloves on.
You notice the panic and the extra ground sheets coming up.
Yeah,
just in case.
So that gives you a bit of an idea of the sort of scale. Dave takes another photo in a minute. Gives you the mystic weights, which we're not giving away. Huge. So this is where we were about to launch it. Now the thing to note about here is, even though there's no wind there, as soon as we get that above the tree line, it really started to pour, and because of its size, and even like 2 and 3 mile per hour winds, it was getting to be a bit. I was a bit worried that the line was going to break because it wasn't that thick a line. But here, so that shows you how slack this balloon is when you launch it. So, and there it is in the next shot. You'll see it's away. So off it went.
And then we had bacon, didn't we?
Yes, we did, yeah. So. And it's just back. Sorry. I've done something wrong. So, being that it was such a great launch, we thought we'd have some up breakfast. We knew it was going to land reasonably close to have like a zigzag path, so we weren't that worried about immediately chasing after it. So Dave and Jude cooked me a nice breakfast. It was lovely, and we were just sort of patting ourselves on the back and thinking how great it had been and how easy the launch was, and we were actually, I think we were about to move. We were listening to the signal. We were about to move when it burst, and it burst at 40 something. I can't remember now. Just a bit over 40 kilometres. So, what's that all about? This is PTE2.
You'd expect a 1600 to go at least that high.
Yeah, you can get higher than 1600. You can see, this is interesting. You can see it filling out there. So this is because it's slack at launch. It's very slow to start with, and then as it sort of like tightens up here, then you get like a more linear ascent rate. But no, we didn't get anywhere near what PT2 did. So yeah, burst early, landed not far away. We went and got it. It wasn't a complicated recovery. 40,877. So. Well, okay, let's go back to that. Why? It's just luck of the latex, I call it. I mean, some balloons burst early, some burst late. I cannot explain a reason that would have burst early, other than it's just luck of the draw with balloons. Some balloons, they're a distribution of burst altitudes. You might get lucky, you might get unlucky, and I think we just got unlucky with that one. So, as we said, it's a pretty expensive shot. I think the balloons are now about, once you've imported them and paid the swinging exchange rate, they work out at about 1,500 and another £200 worth of gas in them. So you've got to want to do it. And then we've done 3. So, although we have shared the costs, and when we have an interested party. Yeah.
Unless somebody wants a commercial launch.
We've got an offer of, we have a definite offer for cash for a sponsorship, but we can't really, they're going to want a record like that.
Yeah, that's the way I see it.
Yeah, if we got a record with it, we'd have taken the deal. But,
yeah. At the moment, we've got no immediate plans for another launch, but we are looking at stuff to get us higher, cheaper, I think, is the way I would put it. Got a couple of interesting possibilities though, which we won't talk about in any depth, but yeah, we may go back to them, we may not. We've pumped a lot of money and not got anywhere as yet. I don't think anybody has, because not even Mark. So, and Mark, in fact, Mark's record is like 3rd place.
Yeah.
So, hey ho. Any questions? Other than, are you mad?
Responsibly, yes.
Right, onwards then. We're overrunning a bit, I guess, but how are we doing with that? So this is our last presentation today. Hopefully, Florian.
Hello, Florian. Can you hear me? Hold on, the sound's not working.
Hello, yes. I can hear you.
Okay. Well, I'm here, the audience is here. I think we can hear you. So the video resolution is not very good, so I will play the videos later on, okay? So you can do the slides first, I'll play the videos later.
Okay. We'll do the videos at the end. I'll just run through the slides.
Yes, please.
Can you see the slides right now?
Yes.
Do they show up? Yeah, perfect. So, my name is Florin Mingereanu. I'm a research scientist at the Romanian Space Agency, and today I'm going to present you a project that we've been working for the past couple of years, a high-altitude unmanned aerial vehicle, intended to be used on high-altitude balloons. And I'll present some data from a test flight that we had in Cape Media firing range, a site on the Black Sea shore in Romania. A short summary: we are a small team of 3 people working on high-altitude balloon flights. Thank you, Steve, for the balloons. We bought exclusively from Random Aerospace, Random Engineering, the balloons, mostly using 1600 grams YA balloons. After the short team summary, I'll show you a couple of recovery issues that we had with high-altitude balloons and why the flying wing UAV was envisioned by us as a solution for the recovery, and some onboard and telemetry data from the test flight that I previously mentioned, and ending up with conclusions. Our team, as I said, it's a small team, 3-person team. We performed a couple of high-altitude balloon flights, standard payloads with trackers, cameras, recovery by parachute, some other payloads having some more advanced equipment in preparation of the high-altitude UAVs. An interesting flight that we achieved in 2012 in Australia was one of the first videos of the total sun eclipse in Australia, Eclipse 1. And it won Astronomy News of the Year in that year. And then several other flights, Astrodome 3, 4, and a series of 5 through 8 aimed at recovering some micrometeorites material from high altitude. Now, the main problem with the high-altitude balloon flights, as probably most of the audience know, is the recovery problem. Typically, the recovery is performed at large distances from the takeoff point. It is difficult to predict accurately the landing position. Indeed, there are ways to predict the landing position, but still they depend on the quality of data and data that you have. And not least of all the reasons, it is also difficult to perform such flights in special areas, for example, small islands in the middle of the ocean, Antarctica, Arctic regions. It's impossible to control the flights to take off in a certain position, A, and land in a certain desired position, B. And at the same time, during the recovery after the balloon burst, or after the separation of the payload from the balloon, the payload exhibits a tumbling and irregular attitude, which for some experiments might not be desired. One example of tracking over Romania, we took off from the position called launch position and ended up 120 something kilometers eastward in the landing position, in a very difficult to access area. It was a wild area for 50 kilometers around that area with very little, very few roads and difficult to access it in general. So for this kind of flights, it would be nice, for example, for the payload to come back to the launch position or to go to a predefined landing area. The solution that we envisioned at the time and we implemented was to fly a flying wing UAV. It's worthwhile to mention that we've been designing and building flying wings at that time for a couple of years for other applications. And in this case, we used a glider flying wing attached to the balloon, as you see in the pictures. And through various test flights, we were able to validate the solution for operational altitude up to 35 kilometers. Using inertial and GPS guidance. It can carry, depending on the size of the flying wing, you'll see on the next slide a couple of more pictures, payloads between half a kilogram to 3 kilograms. There were several flights performed in Finland and then in Romania. Somehow the air traffic is a little bit more relaxed up north over there, and we were able to get some of the initial flights approvals when the system was not validated at that time, a little bit easier. From the top altitude, you can cover around 600 kilometers. So yes, it can glide for around 600, 700 kilometers from a 30, 33 kilometer release altitude. And it has various communication bands. I'll go into details of these communication bands on a slide later into the presentation. We see here two of the wings that we produced. The left one that my colleague holds is a small one that carries around 100 grams of payload. The big red one carries 3.3 kilograms of payload. The entire flying wing is managed and controlled from a ground station. It is worthwhile to note that the flying wing does not need a ground station for operation. This ground station is, let's say, nice to have in order to have the real-time tracking and to be able to upload some commands to the flying wing. But the flying wing can perform the entire flight autonomously. So from the takeoff to the landing, it can perform the entire flight without any radio intervention. The ground station that you see in this picture is a small Pelican suitcase with a composite pylon for the tracking, for the command and uplink antenna. Operations of the high altitude UAV. It is envisioned as being a simple operation. By simple operation, I mean it operates like any other high altitude payload. You attach it to the balloon and take off, and I'll show you the video of the takeoff. No other steps are needed. It is full automatic from takeoff to landing. It has multiple communication link capabilities. These are for various applications. For example, the S-band downlink is for some experiments that could be put on board and might need the S-band downlink. It has a redundant pyromechanical balloon separation. It's a fast and clean separation, and this is important, especially for the cases when the balloon might have an early burst. We have a burst detection mechanism in the autopilot, and it is detecting the burst, and when the burst was detected, if it is an early burst, then it separates the wing from the balloon in order to avoid the tangling of the balloon with the flying wing. Otherwise, if the balloon performs nominally, the separation can be done either by telecommand from the ground, based on a timer, based on an altitude condition, or some other conditions that the client might want to program. It's just a simple program that is installed on board. For the guidance, we use inertially fused GPS data. It is an autopilot that is in-house developed. We are proud about this development because we achieved better than 1/10 of a degree on roll, pitch, and yaw without using ITAR sensors. So none of the equipment on the wing and none of the applications of the wing are intended for dual use or military applications. It is a purely civilian application with commercial components on board of the wing. Take off in very strong wind conditions, and I watched I was very interested about the previous presentation with the very large balloon in high wind conditions, the inflation of that very large balloon. This is a smaller balloon, 1600 grams balloon, but still, if you have a strong wind, it can generate a very bad day when you try to inflate it. Run, because if you have a very high wind condition, you have to run underneath the balloon and allow it to lift the payload without dragging it on the ground. This is the wing, and my colleague was running with it in order to ensure that the takeoff was safe and would not damage the equipment. Flying wing coming back, this is how you typically see it gliding back. We'll see more materials later on. This is the flying wing with the central payload bay immediately after the recovery. In this case, the flight was at around 25 kilometers altitude. This is how you can see from on board of the flying wing. This is 22.8 kilometers altitude, and the area that is pointed by the arrow is called North Mamaia. This is a very nice touristic area on the Black Sea shore, on the Romanian side of the Black Sea shore. The wing at this moment was around 45 kilometers into the sea, north-east. You'll see immediately the trajectory. This is the trajectory. So we took off in A, in a position called A. Then the entire ascent went A, M, B. At B, we issued the separation that was 25 kilometers altitude and around 40-ish kilometers into the sea, northeast. So B is northeast compared to A, in order to get a perspective of the directions involved in the flight. B and A is the entire gliding path of UAV autonomous gliding. As you can see, it can achieve a very straight line, very tight gliding and guidance towards the A position. The position A was the intended landing position in this case. And if you look very carefully near the A, you will see a lot of circles, because the UAV, once it reaches home, it circles long way until it reaches ground level. Of course, it could have glided for significantly longer distance if it was programmed to do so. 2D trajectory, again you can see the red trajectory going from this shore towards the sea, and straighter and with fewer dots coming back home. Fewer dots means that while the position was transmitted at constant times, the velocity over the ground, speed achieved over the ground, varied. Underneath the balloon was 40 km/h, 60 km/h. After separation from the balloon, it was 500 km/h, 600 km/h due to the low density of the air at 24-25 kilometers altitude. The wing achieves gliding within a couple of seconds after the separation from the balloon. Very fast on some onboard data. Up is the graph for the entire flight. For the pitch, we can see near 90 degrees up until the separation from the balloon, and then the pitch stabilizes at 0 degrees. Lower down is the pitch graph zoomed in near the separation. You can see that immediately after the separation, the pitch went to 0 degrees. That means that it achieved a level flight. Let's see the roll. The roll also a lot of rolling back and forth while the wing was hanging underneath the balloon, and then immediately after the separation was in the point denoted with Q. The roll was stabilized to 0 degrees, and then at point R you might see a little bit of more noise on the roll. The reason for that is that at point R the wing already reached a position above the landing location and started to do circles. Doing circles means that the roll is not any longer 0 degrees, so it starts to oscillate at very, depending on the way that it was turning. Again, underneath is the roll graph, zoomed in roll graph near the separation, in order to see a little bit better how the separation dynamic happened. Conclusions. Through the Finland flights and through this flight that was in done in Romania, we achieved a proven solution for a high altitude UAV. While in Romania the flight was at 25 kilometers altitude, in Finland we had flights at 26 and 30 kilometer altitude. Then again we had some other qualification flights at 33 and 34 kilometers altitude. I just showed you the last flight. This flight that I showed you happened this past July 18th. We have payloads between we wrote here, please correct it, 1 and 3 kilograms. 3.3 kilograms, not 4 kilograms for the UAVs that we have. It's just a mistake over there. We have a scalable UAV solution. If one wants a payload of 10 kilograms, that can be done, although you would need a large balloon in order to achieve UAV plus payload 10 kilograms. The wing is sizable. It's not a kit that we bought. Also, the wing is designed and built by us. We have an workshop where we build these composite flying wings. As applications that we envision for the UAV, immediate application, especially for the small one that carries 600-700 grams payload, recovering experimental equipment and specifically recovering radio sondes. With this kind of UAVs, you won't lose a radio sonde, and you don't have to wait until some farmer or some other guy finds it in the woods. It brings it back to you, you change the batteries, fly again the radio sonde. It can be useful for atmospheric probing devices. The larger UAV was used for this. It was used for air core sounding of the atmosphere, basically drills, quote-unquote drills. It collects air, various layers of air from various altitudes. We envision the application to further high-altitude medical development. Also, the autopilot development could be available for other commercial applications. But more than this, we believe that this solution, because it can also be scaled down, not only scaled up, could be a very fast, let's say, entry gate for people into the area of high altitude balloons without the hassle of tracking them and throwing them. It is fun to track payloads. I've done this and I'm doing this quite a lot. But for in some of the conditions, you might not want to track them. As I mentioned, on small islands, Arctic, Antarctica, but also, for example, in the UK, if you fly high-altitude balloons, might be a little bit difficult to track them down, or in some other country. So this could be a complementary solution, let's say widening a little bit the opportunities for the people to get into the area of high-altitude balloons, minimizing the recovery segment. And now I will ask if it's possible to play the movies. I would like to play just 3 videos. First one would be Take Off Cape Media. This is the first video. It's basically the takeoff.
Okay, just give me a second, please.
Yep.
Find out where it's. Okay, what are the names?
Take Off Cape Media rotating.
Okay, got it.
This is the takeoff of the UAV.
There you go. It's playing at the moment.
Okay, just let me know. You'll just see the taking off in high wind conditions. My colleague running with the UAV underneath the balloon. Not to drag it through the grass. The wind was quite strong. Once you finish the video, I'll tell you the other video. The next one that is interesting in my view is the balloon separation. It's just for you to see how it separates from the balloon.
Okay, it's playing now.
Okay.
Oh, it's sweet. Is that a pyrotechnic?
Yes, it's called encapsulated pyrotechnics. So there is no bullets flying around. It's just some substances that does the job fast and safe. And then gliding.
Okay.
The gliding is the video immediately after the separation that contains most of the action with the flying wing falling down for hundreds of meters, keeping the gliding speed at that altitude, which is around 560 km/h. I have the data of the speed in another file. And then it starts to glide back home. You will see some rocking back and forth. That rocking is not due to the autopilot. There is after it achieves gliding, there is significant air current that the wing fills it and needs to compensate real time. Remember, it's a lightweight wing. The entire wing was around 2.7 kilograms with 500 grams of payload in this case. The payload, I will mention what consisted of. There was a complex of scientific measurement systems in pressure, temperature, and radiation, small Geiger. It was built by university in Romania. If the gliding is done, then you can play the last one, which is landing Cape Media. You can see how it lands.
Okay, let me switch over. Landing in Mesa, okay.
Landing Cape Media, yes.
Yeah. Got it. Okay, there we go.
This is a shot on the ground with the wing gliding. It took quite a bit to get, as you imagine, to 25 kilometers altitude, ascent rate around 5.2 meters per second. It went back home from 40 kilometers distance in, I think, less than a quarter of an hour, less than 15 minutes. And then for the entire 2 hours and something, it rotated, circled above our heads until we managed to get eye contact and we achieved a landing on the belly. It can also land using parachutes if that's preferred, but typically, since we don't have a lot to do during the flight, we just watch the screens to see where the wing is. For the landing, we prefer, if we have the right conditions to do it belly landing, at least you get some action. Otherwise, it's completely automatic. With the parachute, you don't do anything, you just punch a button.
Okay. Just give me a second, I can bring the screen up. Okay, we can see you now. Any other videos?
That's it. Thank you. That's all from my side. If there are any questions, I'm more than glad to answer. Comments?
Yeah, any questions from the audience? Well, I think no questions. Thank you very much, Florian.
I think that's it. Yeah. Well, that's the end of the conference, guys.
Take a photo.
Yeah, would like to take a group photo before you leave.
Yeah.
So, if you could, we'll probably do that outside.
Yes, there's a garden outside there. I think outdoors is a place to take photo.
Before you go, though, if you want to take some pizza when you go.